I test this? Is that works?
I can't. Yeah, this is good. Just everything. Yeah, not
speaking.
I can use that one. It's easier. Okay. Yes.
Maybe 1 minute, but I don't know. You're the boss, right? It's my opinion. If people are late, it's their fault. But it's true that most people are.
Yeah, but if people are sort of wandering in, it's
Just have to. How popular do you think this session is going to be? Because if it overflows, we need to stop. To have people basically telling to go to the other room. There's an overflowing room.
it's not going to be full at the beginning.
It's possible it will be. Okay, that's good.
Yes. Where's you ringing that? Isn't the thing too big?
Is this working?
They're handling it in the back.
So what?
They're basically adjusting the thing as you go. So just ready.
Am I good? Can you hear me?
Yes.
Excellent. Yeah, so I think we should get started. It's my privilege to chair the higher order effects session. And the first talk in this session is going to be given by Ugo on model checking higher order effectful programs.
Thank you. Can you hear me well? I hope so. So yes, this is a joint work with Alexis Ghislain, who unfortunately cannot come to POPL this year. And it's about model checking. And model checking, as we know, is one of the most successful paradigms for the verification of programs and systems. And in model checking, what you have is a system M, which can be anything like a process, a program, or just a cryptic structure, if you like. And together with M, you also have a specification phi, which can be a formula in a temporal or modal logic, or even an automaton itself. And once you have M and phi, you can ask yourself whether M is a structure satisfying the specification phi in a logical sense. And this is the model checking problem. And for various forms of systems and properties, this problem has different natures. And sometimes it's decidable, sometimes it's efficiently decidable, sometimes it's even undecidable. And one specific case of this scenario is the one of higher order model checking, in which M is an higher order program, which can be equivalently taken as a higher order Recursion scheme or a lambda y calculus term. Simple types are there, ground types are finite, and you have uninterpreted first order function symbols. So programs produce trees. And then it's natural to take phi as a tree property expressed as an MSO formula or a modal mu calculus formula, or equivalently again an alternating parity tree automaton. And this is a quite difficult model checking problem, which has been shown to be decidable by Ong in 2006, and then reproved decidable in other ways, even, for example, via type checking. The complexity of the problem is relatively high. It's k except incomplete, where k is the order of the program, of the underlying program. But there are tools available which can be used to verify concrete programs. Okay, so fine. So we are interested in going beyond the realm of pure higher order programs as far as the left-hand side is concerned, as far as the class of programs is concerned. So for example, from lambda y or higher order recursion schemes, you can go towards infinite ground types, but if you do so, you are immediately bound to be undecidable because your programming language is equivalent to PCF. You can go towards polymorphic or recursive types. You land into another undecidable problem, but in this case, at least you can find sound, but although incomplete algorithms, verification algorithms. We are interested here in extending the language of programs with effects. For example, we would be interested in verifying that this OCaml program, which is built around two references, R and Q, does not produce any exception. The two references are changed by way of a recursive function, an higher order recursive function in a synchronous way. When at each iteration, the content of the two references are checked by way of the input function G, which just checks whether the content of the two references is the same. And only if it's different, it raises an exception. So it's clear that this program it does not raise any exception. We would like to be able to verify it by way of higher order model checking. The thing is that the literature offers some results in this direction. For example, there is some work about higher order model checking presence of non-deterministic choice, and in this case, well, it's easy to prove that you remain decidable. Sorry. Also, in presence of global store, you can do something. Even the tools provide some features around this effect. In case of exceptions, again, you are decidable. But for example, if you consider probabilistic choice, you are undecidable. There is a paper by myself, Naoki Kobayashi, and Charles Grelois a couple of years ago about that. So there are some discrepancies on the one hand. On the other hand, we would very much like to have a general theory about what is going on here and about which effects gives rise to a decidable higher order model checking problem. So what we do is to consider a calculus in which a reasonably large class of effects can be expressed. So it's EPCF. We follow Simpson and Voneveld in doing so. It's a fine-grained call-by-value calculus with simple types and algebraic operations. And the simple types are such that the ground types are finite. Otherwise, there's not so much hope to get a decidable problem, a decidable model checking problem. Algebraic operations are parametric, and both the parameter and the argument to the continuation are ground and finite. Not so surprisingly, you can prove that the MSO model checking problem for EPCF remains decidable. And this is an easy homework, by the way. You just apply the usual CPS transformation to EPCF. You get rid of call by value. You get rid of algebraic operation, turning them into uninterpreted function symbols. And then you can just apply the old algorithm from usual higher order model checking. The thing is that, is this what we really want? Of course, we can, for example, take our running example, turn it into an EPCF term, and we can verify it by taking a specification phi in MSO. The thing is that, again, is this what we really want? Is it that MSO allows us to verify what we want? Well, in the case of global states, this is the case, but in the general case, this is not always the case. Let's see why. So again, following Simpson and Vorneveld, we can consider an extension of MSO in which the properties we want to verify about effects can be expressed nicely. So this is done by taking set O of sets of trees, each of them corresponding to similarly looking trees. And this is, of course, a way to capture the observation we want to do on the effect tree. And the effect tree, of course, is nothing more and nothing less than a tree of algebraic operations you build when evaluating your effectful program. And each of these elements, each alpha, is then a property we want to check about our programs, and it becomes a modality in MSO. And so MSO parametric on big O is then an extension of MSO in which you can check programs against each possible modality alpha in big O. And this way we can prove that the MSO parametric on O model checking problem for trees generated by EPCF is decidable for certain effects. For example, for global state, exceptions, non-determinism, I/O, and combinations of them. And how did we prove that? We proved that by, for each of these effects, we consider the underlying set of modalities O. For example, in the case of global states, this consists of the modality alpha P, R, O, Q, where P and Q are states. And this modality captures all trees which turn the state P into the state Q along the only, let's say, reasonable computation branch in the effect tree. And the thing is that all these modalities can be captured in MSO proper. So we can go back to MSO proper and use the old algorithm. While, for example, if you consider probabilistic effects, the underlying set of specification is pretty different. It's different in nature. It is quantitative in nature, and it cannot be expressed by MSO proper. Particular alpha greater than P, the modality we need here, checks whether the probability of observing star from unit in the underlying effect tree is greater than P, which is not something you can do in MSO. Okay, so this way we have, let's say, found a way to isolate those effects for which an easy decidability result can be done. And then, and of course, some other effects like probabilistic choice are left behind. This is not, of course, an undecidability proof itself, but it gives evidence that for some effects, we cannot go back to MSO. Is this the end of the story? Actually, no. What we also did was to consider the case of handlers. Sometimes your effects are not pre-interpreted. They are not given an interpretation by way of an external observer, but the interpretation of effects is left to the programmer. And so, as we have seen many times, for example, yesterday, handlers are precisely a way to do so. So we considered that an extension of EPCF with effect handlers, and this can be done in a reasonably standard way by just extending computations with the with-handle construct. And the first argument of the construct is an handler H, which specifies for each possible algebraic operation the actual handler Ci. And this handler Ci depends on both on the parameter X and on the continuation R. And of course, the continuation can be used in a completely arbitrary way. And perhaps surprisingly, we proved that the MSO model checking problem for trees generated this way is undecidable. And the problem is that, again, the continuation can be used in very nasty ways by the handler Ci. And in particular, this allows you to simulate natural numbers as from Plotkin's PCF by way of effect trees and handlers. So what is particularly challenging here is not really simulating natural numbers themselves, but simulate a test for equality, tests and pattern matching on natural numbers. This takes a little bit of an effort to be done. And but the key, again, is the fact that handlers can use the continuation in an arbitrary way, even more than once. You can take a look at the paper to see how this allows you to simulate natural numbers. So, is this once again, the end of the story? Can we do something about programs with handlers? The answer is yes, we can do something, but we have to pay a price, and the price is that we have to consider a very restricted notion of an handler, what we call a generic effect handler. A generic effect handler is an handler in which the handler itself uses the continuation in a very specific way. Okay, so it doesn't mention the continuation itself inside the handler as a free variable, but instead the value of obtained by evaluating the handler is passed to the continuation. And if you do so, you get a decidable model checking problem back. And the thing is that by doing so, by considering generic effect handlers, you get a calculus in which effect trees are transformed in a very disciplined way. Handlers act homeomorphically on trees, and you cannot do the fancy and complex stuff that generic handlers allows you to do. So, summing up, the contributions of this work is to we hope to give a fresh look at the problem of model checking higher order programs with effects, and the take-home messages are, on the one hand, that what matters is not much how you generate trees, but rather how you observe them. How you specify properties of those trees. And the other message is that, effect handlers, can be quite dangerous because they can use the continuation in very nasty ways. This way, you need to be very careful and use handlers maybe in very specific forms. We would like to take a look, for example, in the future about extensions of MSO for which decidability can continue to hold, but of course this is quite this is going to be quite difficult. We are of course thinking about a specific form of probabilistic choice. But we also would like, and this is looks more less challenging, to prove a preservation property about decidability for combinations of effects. And that's it. Thank you very much.
Thank you very much for this talk. We have plenty of time for questions.
Thank you very much.
Yep.
Great set of results. But have you considered local state, and particularly the effect of dynamically allocating fresh names?
Okay, not yet. This is, of course, a very good question. It would be natural to consider them, but we haven't. For the moment, just algebraic effects. And,
They're sort of slightly influencing.
yeah. yeah.
Following up on Andy's question, if you do consider the local state, you might consider the generalization of parameterized algebraic
Exactly,
theories. Have you thought
Yes.
about that?
Yes.
Yeah.
Exactly.
Thanks for the talk. I think for standard higher order model checking, it's efficient in practice. Do you have an idea whether the construction will probably also be similar or something, so this will
Yes.
also hold?
In the paper, we stress a lot about the fact that we haven't, for the moment, considered any complexity issue. So in presence of effects, we don't really know whether the complexity results, the classic complexity result about higher order model checking, hold unchanged or not. We are quite optimistic about the fact that the complexity stays the same. But we haven't done the job yet.
Okay, thank you for the talk. It was very interesting. I actually looked at the proof of undecidability in your paper. And regarding this last slide, have you thought about restricting the kind of programs that you can write so that the model checking problem becomes decidable?
Are you talking about?
How to tame the dangerousness of effect handlers.
So I think that this is a bit what we have done. So we have restricted the class of programs in the sense of restricting the class of handlers very abruptly. We don't know about the middle ground between general handlers and this what we call generic effect handlers, which is again quite restrictive. Look, the result of the handler is just passed to the continuation, and so this is equivalent to really using the continuation in add position once linearly. In this case, the trees are transformed in a more or less homomorphic way, and things work. But we don't know about the middle ground.
Thank you. How about if you allow multi-shot continuation, but you do not allow the kind of structure where you in the proof where you are able to escape the scope of handler and have a recursive function that
I see.
goes over.
Yeah, this is a good idea. Yes, we haven't thought about it. Probably. Maybe CP. We have to check whether a form of CPS transformation can be used there. Probably not.
Okay. Thank you.
Yeah.
I think we have an online question now. Is that right?
Yeah, so there's a question from Discord. This is not the first talk that considers generic effect handlers, continuation only in tail position. I wonder what is the difference in expressivity with just function calls, functions plus dynamic binding maybe?
I don't think we go significantly beyond that. No. We are pretty close to a setting in which handlers are not there, and you try to simulate them, with different means. No. I agree.
So for the handler case, I presume you don't have an undecidability result yet, or only the MSO model checking is undecided, MSO problem is undecidable?
I mean, our result is, in the case of handlers, is this one, so MSO model checking is undecidable.
But do you really need MSO, or can you do with
No, I see what you mean. No. Yeah, it's even reachability is undecidable, yes. Even plain
reachability itself is undecidable.
Yeah.
And in general, do you need MSO, or can you do with first order logic with path quantification?
What do you mean you need for undecidability?
So for modeling all the problems that you have, do you need really
no.
signal logic?
I think that typically, for example, in the running example, I couldn't show it, but with the running example, we need to prove the property I mentioned. you use a very simple alternating parity tree automaton, which doesn't even use parity. So, no, the kind of properties you need. I mean, MSO is is huge. So,
Great. I think we're out of time. Although I'm going to ask you one very last question. So your, what did you call them? Generic handlers. They seem to be the same thing as runners.
I could see. Yeah, I think so.
They are. Okay.
I mean, we with Alexi we struggled a bit about terminology. We decided at the end to use this terminology, but I'm sure there is something
So
else in the literature.
Andre Bauer and Daniel Arman have a paper on runners.
We should.
Okay. Thank you very much. Great. Well, while he gets set up, our next speaker is going to be Martin Elsman, who's talking about explicit effects and effect constraints in, I don't know how to pronounce it, REML, perhaps?
Yes, can you hear me? And now the screen is on. Thank you very much. We are going to talk about reasoning about higher order effects and why this is difficult. One can ask a lot of questions about effects. Does a program make good use of memory? Do two parallel threads execute without allocation and mutation races? Are there any unhandled exceptions? Can a function mutate shared resources? So many kinds of effects. Recently there has been, concretely, there's been a lot of work in combining efficient memory management with multi-threading in ML functional languages, including OCaml, Milton, and so on. And in this context here, for this work, we have been looking at in a world where we don't have a reference tracing garbage collector, but instead rely on the so-called read inference to make sure that we can allocate and deallocate memory in a safe way, and that is based on a static analysis. So, for instance, we can see here the dynamic ray tracing thing going on here. We want to maybe make sure that after every frame has been drawn, there hasn't been any additional memory allocated. So between frames, we kind of know that that all memory is freed before we start working on the next frame. Let me continue here. So let me tell you a little bit about region-based memory management before we go into the work that this is about. So there is a notion of region-based memory management and an explicit version of that, that allows really programmers to be explicit about memory, and that is exemplified in programming languages like Cyclone and Rust. And there you can then program with regions, and you can make sure that it's safe to actually deallocate these things once you decide to do so. In contrast, we can have this idea that we have a non-annotated program, a program that doesn't mention memory effects at all, but where we kind of apply an inference algorithm to insert these allocation and deallocation primitives at compile time. So in this work here, we see that here, for instance, we have memory organized as a stack of regions. So the stack grows this way. First, the first region is allocated, and then other regions are allocated. We can always pop a region from the top of the stack, and we can also allow each of these regions to grow dynamically by using a scheme where we have segmented the regions into pages, and then we can allocate and a new page in each region, and we can then deallocate a whole region in constant time, so to speak, and by using a free list. In this work here, we are going to propose a language, REML, which allows kind of the best of the two worlds. And the idea is to kind of allow for gradual information provided by the programmer to make sure that also after small changes in the program source code, these regions, the region analysis will still kind of give you the same result as in previous runs. So REML is basically taking as a starting point standard ML, and it is actually so that a standard ML program is also a REML program. And then you can start annotating programs with information about regions. So for instance, you can in expressions that allocate, you can specify that some value goes into a region R. You can also annotate types with region information. So for instance, you can say this pair here is a pair of two integers, and it's associated with the region R. So we have this special annotation way of annotating types. And that goes up to also data types and so on. And then we have a way of scoping regions in the programs. These are usually called let regions in the original work. But in order to make it kind of work in the standard ML context, we kind of figured out that there's a possibility of using the with keyword. So now we have a scoping mechanism with these with declarations. So you can specify that a region is kind of locally bound. You can also pass regions as parameters to functions. And then we have this idea that, this possibility that we can annotate functions with, on type schemes and functions with while types, which are basically, and that's another kind of, that was a free keyword again. So it was possible to actually extend and still be totally backwards compatible using these constraints on effects. So now we can reason about effects at the programming level. And concretely, the whole infrastructure here works is based on the MLKit compiler, and that is kind of full-blown compiler for standard ML. So since a standard ML program is also a REML program, it is kind of dealing with an entire language. So a little bit about region inference to begin with. This is work back from POPL'24, and here we have in particular a version of that extended with threads. So we have this let spawn construct. So it's possible to, of course, we are taking as input to region inference a let typed language. So that means that you have to it has to be a well-typed input to the analysis, and then we have a specific way of doing region inference, and that will then annotate the program. So we will see these annotations in the intermediate representation where the analysis has figured out that it can locally bound a region, which is does not appear in the context, and also is not in the type, but only in the effect of evaluating the construct. We also annotate all allocating expressions with these @ annotations, specifying where values should go at runtime. So here's a simple example, and we can consider this where we have extended this region or this language with pairs and box doubles here. So doubles go into regions, and what we see here is that the program is basically just creating a pair in region row 2, and then it's projecting the second element of the pair. So region analysis has figured out that the two regions, row 1 and row 2 here, they're really local to the computation here. Meaning that the stack of regions goes something like this. So first we have a global region row, and then we allocate regions, and this is what the with construct is doing here. So we allocate region row 1 and row 2, and then we allocate this double 3.1 inside row 1, and we allocate the whole pair. Then we allocate 4.2 inside row. So that will go into the global region here, row. Then we allocate the pair, and it points to both of them. After taking the second projection here, we can then discharge the two regions and pop them off the stack. And Y will then safely point to something which is still allocated, and the program can kind of continue. So this is kind of the main idea of region inference, to add these annotations in the entire program. And then, of course, it turns out that it's quite important that functions are allowed to take regions as parameters, because otherwise we get into bad memory behavior. So here's an example here to the right, where we have a function f taking a region as argument. Whenever it's called, it will allocate into its parameter region, the value here. And that means that in any context that f is called, it can actually be called with a freshly generated region. Whereas if we didn't allow regions to be parameters, whenever we would call f, it will allocate into the same region. Right? So it's quite important that we get this idea of parameterizing regions. We have various kind of explicit region support in REML. So we can annotate here. Here we see an example with explicit region annotations with a local region R. We can also allocate into a more global region. It's still sound with respect to the region typing rules. But that's up to the programmer to kind of decide whether that is a good idea. Here we see a region polymorphic function taking R as region R as argument. We can also see that this is gradually typed in a sense that the programmer didn't provide any region arguments down. So region inference will itself figure out that which region to pass to down here. That this is the region R. So that means that it's kind of easy for the programmer to add annotations and still get the desired behavior. So here we see that down is called with a local region R, and then we can this will then be local to the computation after taking the first element out of the list. Okay. We can specify things like region exomorphic functions where for instance we can copy a list into another region, and it's quite important here that we actually remember to call copy in this recursive position here, because otherwise we will have sharing between the arguments and the results, and REML will check that this is not the case. Since we abstracted here, we made explicit that both R1 and R2 here are parameters, and we are explicit about the types, then that will be checked statically. Otherwise we'll get this error from REML. We can have different kinds of functions, also specifying here as a region endomorphic function that will end up allocating its result in the same regions as the arguments lives in. So append, for instance, we will be able to use that in some context where we also make sure to copy the second argument, and if we do so, we will be allowed to actually reason that copy append will create a fresh region or will create an entire new list in a region which is passed as parameter. We can reason about effects also. So here's a local effect which basically is local to the function. So REML can reason that this will never escape the scope here. This makes most sense when we have these wild types, which make it possible to annotate effect constraints. So here we use kind of a separation logic notation for specifying that two effects are disjoints with respect to where they allocate, but we can also reason about where that we are not reading from the same regions. We can also specify other constraints like that some functions should not mutate anything. So here's an example with local mutable storage. So we can perfectly well have local references, and then when we call a function, that will not have any external effect. So here there will be an error since we are updating the global ref here. But if we delete that thing, it will be perfectly safe to have local memory and deal with that. So in particular for this work here, we are doing it. We have support for parallelism, and there it makes sense to get good performance with respect to parallelism. We want to reason that two functions or two parallel functions are really not allocating or racing for the allocation pointer. And this is what the thread library supports, and it's possible to create this par function, which is also is a kind of a standard way of specifying parallelism, where we give two functions and then they are executed in parallel, and then we return the results as a pair created from the result of each function here. So we can specify here that these two effects must be disjoint with respect to the put effects, and that is then checked by REML. We can do a parallel merge sort with respect to that, and here we make use of region inference polymorphic recursion to actually allow for the local calls to the sorting functions to use locally allocated storage. So that is a way of making sure that this runs with as little memory as possible. So there's much more in the paper. We have a formalized type and effect systems with constraints. It has a soundness proof. It's based basically on having a kind of an assertion feature in the language, which is then guarded by these while constraints or these effect constraints, and then we can show that they never appear at runtime. There's a rich description of the implementation, and then we show some larger benchmarks, and we also discuss extensions where we can combine the effects with exceptions and other kinds of effects. And some of that is still, of course, future work for the implementation, but yeah, and lots of related work, of course. So thank you very much.
Thanks, Martin. Do we have some questions?
Yeah, thanks, Martin, for a very interesting talk. James Noble, now creative research and programming, and I'm a recovering professor. One thing I noticed looking through this, and it's sort of really interesting work, is the constraints you seem to have are just disjointness constraints, whereas things like Rust and other ownership type systems typically have an ordering over the regions.
Yes.
Have I missed something, or?
I think you didn't miss anything. There's no outlives relationship on regions here. Everything is based on a unification model. This is something that we could consider adding, but for region inference to kind of work out, we would like to not have that being part of the inference, but maybe that can be at special points in the program. You might be able to say, this is an outlives relationship here, and then region inference doesn't need to kind of try to add those every place, but can deal with it locally. And that is definitely, you can have some examples where it shows that we don't have the outlives relationship, but where we're kind of getting a little bit too conservative on the estimates.
Yeah, if you want, sorry.
Hi, Arthur Chaillot from Inuria. Thanks for the talk. I had two quick questions. So the first one is about the status of the region handle at runtime. Are they erased, always, never, sometimes?
So the story is we have added, there's other work that also adds a reference tracing garbage collector to the whole setup, to the NML kit. For that to be kind of bootstrapping and so on, which it does, a reference tracing garbage collector needed in particular for these global regions. Mm-hmm. We also added some, generational collection and, and saw the differences between adding regions and generations. it seems to be kind of dual approaches to figuring out what to deallocate. So the story about the global regions, that's definitely much more to do there, and for using static techniques to try to deal with some of those. But for the more local ones, region inference actually does a quite good job at reusing memory.
We get the next speaker up while we continue.
I was curious about the list of list type. Do you control the region for the outer list and for the inner list separately?
Yes, so it's very, region inference will really add, be very, it won't join regions unless it really has to. So it's very segregated kind of, and then of course from an optimization point of view, you might sometimes want to actually join because it's cheaper just to allocate one region than it is. But on the other hand, the lifetimes might differ.
Okay, we have time for one more online question.
So there's the online question is, can region and effect annotation be used to relax the value restriction?
That's a good question. I haven't thought about that. I doubt it a little bit, but then yeah, I will have to look further into that, whether that can be used to get rid of the unsoundness of a language without the value restriction. I guess is the question.
Okay, thanks, Martin. Let's thank Martin again. And the third talk in this session is about decalf, a directed effectful cost-aware logical framework, and Harrison is going to present this.
Is this microphone working? Cool. Alrighty, hi everyone. Thanks for the introduction, Sam. I'm excited to talk to you about some work that I've been doing with my collaborators on a new version of CAF. I'll note that this is building on prior work on CAF, which is a cost-aware logical framework, but I won't assume any prior knowledge on that, so I'll just give you an overview of the full story. So first off, some motivation. You're all familiar, I'm sure, with the list map function, but when you think about cost analysis, you might realize that this is tougher for map than it might originally seem, because map is a higher order function, and the argument f might perform effects. So it's not immediately obvious how you would analyze map. So decaf, which is a type theory embedded in AGDA, will give us an elegant and linguistic answer to this problem. So first, let me tell you about the core language. There are three essential components. The first one is the use of effects. The second, which is new in decaf, is this notion of judgmental program inequality. And then finally, we have a phase distinction, which is inherited from CAF, and we extend it to interact with the program inequality here. So first off, CAF builds on call by push value. So we split up our type theory into value types and computation types. Computation types are interesting because they let you perform effects at those types. F of A, just for notation, means that you're computing a value of type A, but you might perform some effects to do it. And the nice thing is, yeah, the computation types on the right let you incur effects, and they also retain some nice reasoning principles that we'll use to prove properties. So we add an effect called step to the C, which means that you should incur C units of abstract cost. So when we write step to the C of E, that means incur C units of abstract cost and then run program E afterwards. Here C is an element of some monoid, like the natural numbers. And there are these expected laws saying that, for example, if you incur 0 cost, then you might as well not bother. And if you incur C1 cost followed by C2 cost, you can consolidate those using the monoid structure. So in CAF, we had a notion of exact cost bound. And the idea is that to show a cost bound, you use program equality. So if you want to show that a program E of type f of A has cost C, you show that there's a value A such that E is equivalent to the program that incurs C units of abstract cost and then returns the value A. So for example, in merge sort, you know that for all lists L, merge sort of L has cost length of L log length of L, informally n log n. So in decaf, we add a new notion, which is program inequality. E is less than or equal to E prime, where both E and E prime are computations of type X here. And the intuition is that E and E prime compute the same result, but E might be cheaper at doing it. So for example, the program on the left is less than or equal to the program on the right, because they both return the same result, but the left one costs 3 and the right one costs 12. So here, inequality is verifying cost and behavior simultaneously, which we'll find important in a little bit. And this is also inspired by directed type theory. This is a similar notion of inequality, just to note. So similar to the slide before, we can now talk about inexact cost bounds using inequality, where we say that program E is bounded by a cost C when there exists a value A such that the program E as an entire program is less than or equal to the cost-bound program that incurs C cost and then returns the value A. So now, for example, we can bound something like insertion sort. Insertion sort doesn't always incur the same amount of cost. It's cheap on a sorted list, but very expensive on a reverse sorted list. But in any case, the cost is always bounded by length of L squared. So just to compare equality and inequality, they're actually quite similar. They're both reflexive and transitive. Equality is interesting because it's symmetric, whereas inequality, of course, isn't. They're both, well, equality is a congruence and inequality is a monotone. Different terminology for similar ideas. And they're both pointwise on functions. So since we have these nice reasoning principles, we can now compositionally analyze program cost using inequality reasoning. So I mentioned our type theory is embedded in AGDA. This means that we can write some code in call by push value and prove properties about it. So using the insertion sort example, here's the auxiliary function insert written in call by push value, where we track 1 unit of cost per comparison. And we can prove the theorem that this insert function is less than or equal to the function on the right that just takes in an element, takes in a list, and incurs length of that list cost before returning some specification level sorted list. In order to prove this, we can just use a chain of inequality reasoning. So I'll show you an example case of the proof. To show this theorem, you would start with the code from insert on the left, and you would use, for in this example, monotonicity and the inductive hypothesis to simplify the code, and then some other properties about equality will get you to the desired form. So now I need to tell you about the third key component, which is this phase distinction, inspired by work by Sterling and Harper. So the extensional phase is a proposition that we have in decaf, which isolates the behavior of a program. If this proposition X holds, then 2 things happen. First off, you know the cost model is trivial. And second of all, you know that inequality implies equality. And we have a modality open of A, that's just the function space out of the extensional proposition, that isolates the behavioral part of a type A. So as a corollary, we have this theorem called non-interference that says if you have a type that whose behavioral part is trivial, then every function out of that type into open of B, into the behavioral part of B, is a constant function. The punchy way to say that is cost does not impact behavior. There are some other corollaries. So for example, if the extensional phase holds, you know the cost model is trivial. So every cost is actually just equal to 0, since you know you have a monoid. And therefore, incurring C cost is the same thing as incurring 0 cost, is the same thing as not incurring any cost at all. And using this kind of reasoning, we can prove good theorems about the behavior of programs, such as, well, as long as you're willing to discount cost, insertion sort and merge sort are actually just the same thing. So now let me tell you about effects, which we add in decaf. So decaf supports a variety of algebraic effects. In the paper, we have a bunch of examples, but for the purpose of this talk, I'm going to focus on probabilistic choice. So to add a probabilistic choice effect, we add a primitive just like step. Here we call it flip, which is like a weighted coin flip with probability p that you land in one branch and 1 minus p that you land in the other. This is pretty standard. Using this primitive, we can then define randomized algorithms. So for example, we can define the randomized parallel quicksort algorithm, which takes a list and returns an f of list. And remember, f means that you can incur some effects. So in the process of sorting, it's going to flip some coins and incur some cost. This is, by the way, benign randomization, so it's only for the purpose of getting a good cost bound, but the same value is always returned. Therefore, we can specify the given bound, which is a worst-case upper bound for quicksort, saying that quicksort, regardless of how the randomization shakes out, will take in a list L and incur at most length of L squared cost before returning the specification level sorted list. And this proof is just by induction. As a corollary, we can use the extensional phase to notice that quicksort behaviorally is just taking in a list and returning the sorted specification, the sorted specification list. So this is just using the bound from above, knocking out the steps because of the corollary we saw, and replacing an inequality with an equality. Now for a more interesting example using effects, we have a simple algorithm that takes a random sublist of a list, keeping each element with 50% chance. And then if you keep the element, you incur 1 cost. You would hope to bound this by something like the binomial distribution, which is very similar to the sublist program. Here we take in a natural number, and then we compute an f of 1, which is really just a cost. And this is an implementation of a program for the binomial distribution. You'd hope to compare these programs and say that sublist is bounded by binomial, but they don't have the same type exactly. So we define an auxiliary function that will help us deal with these kinds of cases. So we have this result erasure, which just takes an f of a and gives you an f of 1 by deleting the a result. And this is useful when you only care about cost and not the behavior. So we can then say things like, well, the function that takes in a list and gives you its result erased sublist, in other words, just the cost incurred by sublist of L, is the binomial distribution on the length of L. And as a lemma, you might know that the binomial distribution on n is upper bounded by n cost, so you can give this upper bound as well. Now let me bring us back to list map from the very beginning. This is adjusted for call by push value now. As I mentioned before, if f is allowed to perform arbitrary effects, there's really no hope for doing anything good. It's possible that f could be flipping coins or messing with mutable state. The order in which the recursive calls happens could matter. This is, it's not really tenable to expect a good bound. So there are a few options. The first one is to just give up. You can give a trivial bound, but this does mean something. This is saying that map, if you don't make any other assumptions, costs what it costs. So when you're working in decaf, you can use reflexivity to say, yeah, this program just costs itself. And if you want to understand how this works, read the code. However, if you have some simplifying assumptions, you can give better bounds. For example, if you know that the cost of f is always bounded by a constant c, then you know that calling map on f in a list is bounded by c times the length of the list cost. So this sounds more like the O of n bound you might be expecting for map. But in the presence of effects like randomization, you can also say more advanced things like if f is bounded by the binomial distribution on n cost, then map fl is bounded by the binomial distribution on n times length of l cost. So you can give these more advanced bounds. All right, so let me briefly talk about the semantics in my last couple minutes. So we give a topos theoretic semantics that's based on directed type theory a little bit. So it's also based on synthetic domain theory. So we're defining a path relation in the semantics, assuming that we have some interval object. And this is just saying that you have a map out of the interval such that the left endpoint is x and the right endpoint is y when you expect x to be less than or equal to y. And hopefully we would satisfy all those properties we saw earlier. But a priori, this only is a reflexive and monotone inequality relation. So we have to do a little bit of work to make sure that this is transitive pointwise on functions and extensionally discrete. To make sure that it's extensionally discrete, we can just ask that the interval be extensionally trivial, because then any map out of the interval is going to be a constant. So the left and right endpoints will be the same, and therefore you have your equality. So that solves one problem. And to solve the other problem, to get transitivity and pointwise on functions comparison, then you realize that there's just a reflective subuniverse of types for which this does hold. So you can, instead of working in this larger category, just find yourself in the reflective subuniverse. And then you get the last two properties that you want. So for a non-trivial model, here is a summary of the axioms we need. We need an interval object I. We need a discrete type of natural numbers, a proposition x, and we need it to be the case that I is extensionally trivial. And the model that we have in the paper is augmented simplicial sets, which is like simplicial sets, but where you have an additional initial object, -1, in the simplex category. Then you get that the interval is the unate embedding of 1, and the extensional proposition is the unate embedding of -1. So now if we wanted a cost model like we had earlier with the natural numbers, we can define it as a directed QIT, where you have this type omega that has, for the natural numbers, 0 and successor constructors, but you have this directed condition such guaranteeing you that n is less than or equal to successor of n. And to make sure this is a valid cost model, you check that extensionally this is trivial. Cool. So now let me conclude. There is plenty of future work that this opens. This is really the start, not the end. This helps us understand how we can analyze algorithms in this synthetic way. And for example, we hope to analyze, do amortized analyses, building on some work that I did with co-induction. We hope to support data abstraction and cost signatures, and maybe even separate the cost proofs from the correctness proofs. We hope to study more effects and do a deeper dive into parallelism, and even consider non-algebraic effects, such as unbounded recursion. We also hope to consider probability more in more advanced cases, such as doing expected or with high probability analyses. So to conclude, CAF started off by doing synthetic cost analysis mostly at these F types, the free algebras. And decaf adds support for general effects and higher order programs. It lets you compare programs using inequality to get these inexact bounds. And it's harmonious with the extensional reasoning, so you can turn cost bounds into correctness theorems. And to justify this, we have a topos theoretic semantics in the topos of augmented simplicial sets. And we have practical examples embedded in our AGDA development. So with that, I think I'm just about out of time, and I'd love to take some questions.
Do we have some questions?
Hi, so I had a question about your semantics, your topos semantics. I'm aware that call by push value semantics often have a junction between two things for U and F.
Yep.
Being able to, in your semantics, have you identified what this adjunction would be?
Yes. Yeah, so the category of augmented simplicial sets is where the value types are living. And for talking about cost, we just use the writer monad on that category. And the category of algebras for the writer monad is the category of computation types. I think that's pretty standard with call by push value.
So there is a question from Discord.
Sure.
Could you get an infinity cost for upper bounds by making your cost QIT co-inductive somehow?
That's an awesome question that I would love
Thank
to
you.
think about more. I don't know.
Yeah, so did I understand this correctly that types, the cost does not appear in the types?
That's right, the cost does not.
Yeah, so is there a reason why you chose to do this? Like there are frameworks which actually embed cost within the types or grade them with the cost. So have you tried comparing, or what is the reason for doing?
Sure. I think so maybe the intuition I can give is we're working in a dependent type theory, and we're here a cost bound is just another program. So rather than saying that you have a cost, rather than putting the cost in the type, we want to have the cost bound be just another program that you're comparing to that can have arbitrary effects involved, which could be cost, but it also could involve randomization, for example, like with the distribution example. I think this is more general, although I would have to think a little bit more before saying that definitively. Thanks.
I was kind of curious about your inequality. It's kind of an equivalent of the propositional inequality, which usually has some sort of transport operation. Do you have some eliminator for your preorder, or is it just there for the sake of counting things and there's no way to eliminate it?
We don't have an eliminator at the moment. At least extensionally, you know it's equality, and then you can use the eliminator. But intentionally, I don't think we have an eliminator, and I don't think we ever would need it. I'm not sure.
I would expect it to be a bit more annoying, because then you need to think about like covariant and contravariance of the predicate or something like this, which is one of the nightmare of directed stuff. So
yeah,
okay, thank you.
I think we might have avoided that, luckily.
I have a question.
Sure.
Did you consider handlers of effects?
Handlers? Not at the moment. But it would be cool to figure this out.
Okay, any final questions? No? Okay, in that case, let's thank the speaker again. And I believe the final talk in this session is going to be presented remotely.
Okay, for sure. Thank you.
So hopefully we can get that set up. Assuming the technology works, this is going to be on modular denotational semantics for effects with guarded interaction trees. I don't know who Lars, is it going to be Dan? Yeah, Dan Frumin is going to present this.
Hello everyone, can you hear me?
We can hear you, but we can't yet see your slide. We can't yet see your screen. Can you hear us?
They're online. They haven't shared their screen yet.
We could hear him, but he apparently couldn't hear us.
Yeah, because we haven't switched it yet because they haven't.
It sounds like there is a very long delay.
You need to share your screen. You need to share your screen. Uh-huh. Aha. Okay. So when you're ready, I guess this might be in about a minute's time. Dan, can you commence your talk, please? Uh-huh. Aha. Okay. So when you're ready, I guess this might be in about a minute's time.
He should be able to hear you now.
There's a very long delay.
Right?
There's a very
Oh,
long
I
delay.
can hear you now.
Oh, you can hear me now and it's instantaneous, is it?
I guess 1, 2, 3. Is this instantaneous?
Yes, this is great. Go ahead, give your talk. If you're ready now, Dan. Yes, great. So Dan is going to give the talk on modular denotational semantics for effects with guarded interaction trees.
Yeah, thank you, Sam. So indeed, and first of all, I would like to say that this is a joint work with Amit Timani and Lars Birkedal. Both of them you can find in real life at POPL. So let me start by first breaking down the title. Our work is concerned with denotational semantics, as opposed to operational semantics, for example, and by denotational semantics we specifically mean compositional, syntax-free, or almost syntax-free representations of programs and computations with higher-order effects, for example, input-output or higher-order store. And we want our approach to be modular, in the sense that we want to be able to represent and reason about different effects separately and then combine that together. And finally, to achieve this, we introduced the framework of guarded interaction trees, which we fully formalized in COC and applied to several case studies. So as it might be evident from the name, our framework takes a lot of inspiration from the work on interaction trees. Interaction trees, which can be seen as a co-inductive version of free monads, it's a framework for representing computation for the effects as possibly infinite trees. And most importantly, it comes with a very rich and honestly like very impressive Coq formalization that has already been applied in many different examples and case studies and so on. However, that framework is tailored and designed towards working with first-order computations and first-order effects. And one way to look at our approach and our work is that we kind of provide a higher order version of that. And so to get you some idea about interaction trees, let's take a look at this example. Here you can see the tree that represents the following computation. The program first reads an integer from the standard input, and then based on whether that integer is even or odd, it outputs 0 or 1. So here, for example, in this branch, we input number 2. This is an even number, so we output 0, and then we terminate with exit code 0. So this interaction tree is parameterized by an effect signature. In this case, we have two operations, input and output, and they both come together with input and output arities. So for example, the input operation takes no arguments and produces an integer. So its input arity is the unit type, and its output arity is the type of natural numbers. Now, with this signature, we can see that the nodes in the interaction tree correspond to effect operations together with their arguments. And branching in the tree, well, that corresponds to the output arity. So, for example, the output arity of the input operation is a type of natural numbers. So that means that for each natural number, we have a successor that represents the continuation of this computation. Okay, so this is kind of a specific example of interaction trees. In general, interaction trees are given in Coq as a co-inductive type, but it's useful for our purposes to think of it as as the largest solution of a particular equation. And this equation has three components. So the first one is the ground type, which we pick to be integers, but I mean we can pick any ground type there. The second component represents a silent step or an internal step of computation, which is needed for technical reasons. And finally, the third component is actually used to represent effects. So each effect I comes with an input arity, which represents the argument, and the continuation, which sends the output arity to interaction trees. So for example, for the input operation, the output arity is a type of natural number. So the continuation is going to be just functions from natural numbers to interaction trees. And this is exactly what represents the branching. So now, suppose we want to add higher order computations or higher order effects to this. Well, what we could do is we can just add another component to the equation. But this is not going to work, because in this equation, we're going to have negative occurrences of recursion. And so this equation does not determine an inductive or a co-inductive type. So we cannot solve this equation using inductive or co-inductive types. So our idea is to go into a more extensive setting, specifically guarded type theory, where we know how to solve equations like this, right? And well, if you don't know about guarded type theory, it's not really important. The only thing that you need to know is it's a kind of type theory where you have a particular functor later, which we denote with this black triangle. And the two important bits in guarded type theory is that we have guarded recursion using this kind of guarded fixed point combinator. And what is even more important for us is that we have unique solutions to all guarded equations of types. So to equations of the form x equals f of later x, where this later x can appear in any position, both in negative and in positive positions, but this x has to appear under the later modality. So this makes it guarded, right? So now with this, we can actually define our type of guarded interaction trees as the unique solution to a particular equation. And here we can see we still have a number of components. So we still have the component that corresponds to ground types, which again, for simplicity here, we take to be natural numbers. We have a component that corresponds to a silent step of a computation. And we have a new component that corresponds to functions to represent higher order computations. And this here you can see this component is guarded. So we are looking at not just functions from guarded interaction trees to guarded interaction trees, but from later interaction trees to later interaction trees, right? And we need this to make sure that this equation is actually guarded. Also, we add another component that corresponds to representing explicit error state, will be quite useful. And finally, we have the component that corresponds to representing effects. And here you can see we modify the input and output RTs so that they also take the type of guard interaction trees as an argument. And this is necessary for representing higher order effects. So for example, if you want to represent higher order store, we want to have operations read and write. For example, the read operation takes a location and reads the value that is stored at this location in the heap, and it produces an interaction tree. And so if you want to model those kind of effects, you need to modify the input and output RTs to allow this. So this is quite a crucial change. Now, with this definition, we can actually represent, we can interpret untyped lambda calculus with effects. So we have the combinators that allow us to embed, natural numbers, functions. We have a combinator that computes function application and so on. However, the effects are not really interpreted. They're just represented as is. As effects without handlers or whatever. But in order to give full meaning, to full semantics to the guard interaction trees, we actually need to be able to interpret those effects. And we do so as follows. So we assume that every effect signature comes with a verifier. So what we mean is that for each effect signature, we have a type state, which represents the internal state that we need to interpret the computation. And then for each operation, we have a verification function, which essentially computes the output RT from the input RT using the state monad with this internal state parameter. And one way to think about it, it's quite similar to what Ugo described in the first talk as like this generic effect handlers, right? So we don't involve the continuation at all, we just compute the output RT from the input RT. And if we have those verifiers for all the effects, then these determine reduction relation on guard interaction trees, or rather on pairs of guard interaction trees and this internal state parameter, which tells us how to execute those operations. So for example, for the higher order store, we can take the state parameter just to be the type of maps from locations to later of guard interaction trees. And if we write down the verifiers, in the most standard way, then we get the kind of reductions that we expect. So for example, if we have a guard interaction tree that first writes alpha to the location L and then proceeds as beta, and we are looking at this tree in the state sigma, then, well, this reduces to the continuation beta, and it results in an updated state where we actually assign alpha to the location L. Okay, so this gives us the semantics of guard interaction trees, and we actually want to reason about the semantics, to reason about the behavior. And my favorite way of doing this is through making a program logic. So more specifically, what we do is we make a separation logic for guard interaction trees based on Iris. For those who don't know, Iris is a powerful high-order separation logic with an extensive formalization. You might have heard about it during some other talks in POPL, like there were some sessions yesterday and probably today as well. But basically, you can think of it, it's a framework that allows us to derive custom separation logic for different use cases. And in our work, we instantiate Iris with the guard interaction trees, and we get a separation logic. So we get all the usual connectives like separation, conjunction, magic wand, and so on. But of course, the most important connective is the weakest precondition. And so the weakest precondition for a guard interaction tree alpha and the predicate phi, it states that, first of all, this guard interaction tree alpha is not an error, it's not in an error state. And whenever it reduces to a value, so whenever it cannot reduce any further, this value is going to satisfy the predicate phi. And this is a quite reasonable, quite standard reading of the weakest precondition, similar to what you would expect from separation logic for a normal programming language. And in fact, in our separation logic, we have all sorts of normal rules, structure rules that you would expect. But of course, the most interesting rule of our program logic has to do with effects. So here I have the version of this rule for effects that is specialized to the write effect. So here, once again, we have this computation that writes something to location L and then proceeds as beta. And if you want to prove something about it, we need to prove two things. So first of all, we need to provide a predicate has state, sigma, which says that the internal state for this store effect is sigma. And the second thing that we need to do is we need to provide a proof of beta, so of the continuation, assuming that we have an updated state where we actually written alpha to the location L.
5 minutes.
Now, so this is a symbolic execution rule for the write operation. And those of you who are familiar with separation logic might be thinking that this rule looks very suspicious. And this is because it talks about the whole the whole heap sigma and not just about this specific location L. But luckily, using the mechanisms of Iris, we can derive the more standard rule, which we call the local rule, which talks just about the location L and not about the whole state sigma. And I just want to stress out that we can derive this just in Iris without knowing anything about guard interaction trees and so on. And in fact, we can completely recover the standard looking separation logic for imperative programs just from this one generic rule and the logic that we have. And I guess the point that I want to make here is by utilizing Iris, we can derive different domain-specific logics from different effects just from one separation logic that we have for guard interaction trees. And of course, we have to have this global version of the rule because, well, in this case, we know that sigma is a heap, so we know how to separate it into individual locations, for example. But if we're talking not just about store, we're talking about arbitrary effects, this parameter sigma is just some state that is provided, that is decided by the user. So the logic doesn't know how to split the sigma into different things, so it's up to the user to do this work. But luckily, the user can do this without breaking the abstraction of the program logic or anything like this. All right, so now we can finally put all these components together in one of the case studies that we did. And this is a case study about cross-language interaction, which I think showcases kind of the nice thing about domain theory and the nice thing about the modularity that we did. And the setup of this case study is as follows. So we have two programming languages. So first of all, we have lambda calculus, simplified lambda calculus with recursion, integers, and input and output operations. And the second programming language that we have is affine, or linear lambda calculus, where we have linear functions and linear references with like strong update and things like this. Now, we can interpret both of those languages separately in guard interaction trees. And once we interpret them in the common target, we can start talking about, okay, how do those things interact in terms of their semantics? But of course, we have to facilitate their interaction somehow. And we do this through these two embedding functions. So these embedding functions allow us to move values between two languages. But of course, we cannot just, for example, take a linear function from one language and use it as a normal function in a nonlinear language. So when we move values between languages, we have to protect them. So for example, if we move a function, we have to wrap it in some kind of runtime check that monitors linearity relations at runtime. And now the question that we want to settle about this system is that we want to prove that this combination of languages with the embeddings is memory safe. And this is how we do it. So first of all, we prove separately that the interpretation of the two separate languages is safe. And we do this by constructing two separate logical relations models using the program logic that we described before. And we do this completely independently of each other. Then we prove that the embedding functions actually move those things between the models in a memory safe way. So what we mean by this is that embedded terms, they can raise errors, but the only error that can raise is a linearity exception. So an embedded term cannot raise a memory error, for example. It cannot dereference a null pointer or something like this. Then we combine those things together to prove that the combined system with embeddings is memory safe. And we do those just by combining the logical relations from the first two points and the proof of the third point into one model. And I want to say that when I say combine, I don't mean it as a metaphor. I don't mean it, in some abstract way, like the proofs are similar or something like this. No, I mean it in a very direct way. So we formulate the first two models separately and independently of each other. They don't know of each other. And then we can put them together, literally reusing, the same definitions, proofs, and co-identifiers. And we believe that, well, this generally allows us for a great proof reuse. And we believe this validates the sort of the modularity of our approach. So, well, since it's already the break time, I would like to thank everyone for listening. If you want to look at more examples and details, please check out our formalization and our paper, and I would be glad to take your questions.
Thank you very much. The break has just started, but I think we can still take some questions. So,
hi. Thank you for a lovely talk. One of the things that you had on slide, I think 4 or 5, was that there's a silent step for your interactions trees. Could you give us some kind of
Yes.
intuition as to why that silent step is needed in there?
So I can give you, so a more philosophical reason is that, well, for guarded interaction trees, or for interaction trees in general, we want to talk about things like, compare programs modular, some kind of internal steps. There's also a more technical reason for this, is that, so because our functions are guarded, when we apply a function to an argument, the result, we don't get an interaction tree, we only get later of the interaction tree. And then, so then we need to embed this somehow, interaction tree, into the general type, and this results in kind of a silent transition.
So there is an online question. Do you need this higher order constructor to model higher order functions, or rather higher order effects? I thought we could do higher order functions with first order trees, as in game semantics, for example.
Yeah, so we need this function for higher order, for representing functions. We need this for representing higher order functions in a more in a semantic way. You can still, there are some tricks that you can do to represent higher order computation interaction trees, but this involves working with closures, or it involves some kind of syntactic techniques, where this is just a more straightforward semantic way of doing this. But more importantly, for higher order effects, not just for computations, this corresponds to having this interaction tree parameter over here.
Go, Steve.
Sorry, this is Steve Zdanchuk from Penn. Thank you for the very nice talk. One of the benefits of interaction trees is that you can extract executable programs from them, but I noticed your handlers were into prop, so I'm wondering what the story is for extraction of executable programs is for guarded interaction trees.
Right. But so our handlers are not actually into prop, so they're just calc functions, let's say, but nonetheless, we still have some problems with extraction, and this mainly has to do with the fact that we are working with this guarded type theory on top of calc. We have a hunch that it is possible somehow to abuse the calc extraction mechanism hard enough to be able to extract those stuff, but we haven't been able to actually do this in practice, unfortunately.
I have a question. So you had this restriction on, I think you called them the arrayifiers.
Yeah.
Have you thought about relaxing that? Could you do, I don't know, things like concurrency or using continuations multiple times?
So, yeah, so that's a very good question. So indeed, right now, our verifiers or handlers or interpreters, whatever you call them, they are very restricted. If we allow the verifiers to also handle the continuation, to do something with it like discarded and so on, then we will be able to model things like continuations and so on. But this will introduce some changes to the logic and will limit some of the reasoning principles that we have. So this is something that we definitely want to look into, but we haven't done that.
Okay. Thank you very much. One last question.
Hello, I had a quick question about, I was actually going to also ask about control effects as well, but I was also wondering, the domain of interpretation seems to be fixed in this case. Is there ways to generalize it, or was it fixed for examples in this setting? So is there also a reason why you added the error node for this case?
Yes, it did. So you're completely right. This is a fixed domain, just like you would expect in domain theory for untyped lambda calculus. And this is also the reason why we have this error domain, because we might have some kind of error. So for example, if you take a natural number and we apply it to another natural number, that results in there, right? Because we can only apply functions to an arguments, and that was a more of like a design choice that we wanted to have like one universal domain where we can interpret all sorts of stuff.
Okay, thank you.
Thanks. Let's thank the speaker again.
Thank you, Sam, for doing this.
Okay, am I on here? Is it good? Yeah. Yeah, okay, so this is about probabilistic programming, as is the session. This particular talk is about probabilistic programming as a way of statistical modeling. So a way of describing statistical models by writing programs, and the focus is random graphs. These are three methods that we're using to do this: Markov categories, graph ones, and nominal sets. You'll see a bit about it as we go through. I've got all these brilliant co-authors, of which Hongsuk, Cameron, and Sean are here, and the others might be online, or you can find them elsewhere. This project that's been going on for quite a while, maybe 6 or 7 or 8 years, so that's why we've accumulated, I guess, quite a few authors. Let me show you the main theorem, and then we'll chat a bit more about random graphs. Okay, so the main theorem is this. The following data are equivalent. A well-behaved implementation, I'll say what well-behaved means, of a particular abstract type, and a graphon. Okay? Now, the abstract type is an abstract type of graphs, so it has a type of vertices which we can implement however we like. Is there a laser? No. Right. And then it's a generative graph, so we can generate new vertices. That's why there's this new, which gives us a new randomly a new vertex. And it's a graph, so there's an edge relation. So two vertices, is there an edge between them? Okay. This is in a probabilistic programming language in some sense. And on the other hand, a graphon. So graphons have been rediscovered several times over the last 50 years in probability theory, in combinatorics, in graph theory. One view on graphons, and we'll come to this a little bit, is it's a function from the unit square to the unit interval. So we can draw it as a kind of heat map. Here are two heat maps. There's a lovely book by Lovash about this concept. Okay, so these things are the same, that's the point. So you have like a programming view on graphons. Let me dig in a bit more about random graphs then. Okay, so high level, random graphs are interesting for all kinds of reasons, modeling all kinds of networks, social networks, a physical network for disease modeling perhaps, biological networks or graphs, molecular structures, but also lots of things can be encoded as graphs. So equivalence relations are graphs, so we can understand clustering in terms of graphs, finding which things are roughly the same. And then, as I said, it's not just a practical thing, there's also deep connections to combinatorics and graph theory. Let me show you my view to hone in a little bit. We've been developing a language called, or a library called Lazy People, Lazy Probabilistic Programming Language. And this was the idea was to investigate kind of stochastic processes and infinite probabilistic structures from a programming point of view using laziness. So that has all kinds of stuff in it, but one thing we can talk about is graphs. And here's an inference thing I did. You can read the code here, it's literate Haskell and it's not very complicated. Given the graph on the left, suppose we found it in the wild by measuring something, where did it come from? And we can infer, perhaps it came from a geometric situation, right, with quite a high likelihood, where you can see this is actually the graph, the same graph, but it's now mapped onto the sphere, and points that have edges between them, vertices that have edges between them, are close. Okay. So these are the kind of questions you might ask. Let's zoom in a little bit more on this interface then and talk about that to be a bit more, even more concrete. So the interface we need to implement vertex somehow. We need to say what's new and what's edge. So here's an example of an implementation, but there are lots of implementations. The point is to explore them. This is a geometric one, like we just saw a second ago. And here the vertices are points on the sphere. So we could implement that as x, y, z coordinates, or Euclidean coordinates, or polar coordinates. There's different ways of doing it. Here's pseudocode. You can read the actual implementation online. So new randomly picks a point on the sphere. And let's do it uniformly. So we uniformly pick a point on the sphere, and that's a vertex, a new vertex. There's an edge between two vertices if the distance between them is less than some parameter theta. Right, if and only if the distance between them is less than some parameter theta. So we can then randomly sample. Here's a random sample with, I think, 14 vertices. And theta was picked to be pi by 6, and it's a 3D sphere. But we can vary those things. And what you saw earlier was an inference problem, and we inferred that theta is about 60 degrees for this particular graph. Okay, so that's one implementation. But probably looking at this, you can imagine other implementations of this interface that would be quite useful. For example, other shapes, not just a sphere, maybe a torus or a cube or a tetrahedron or something more wacky, right? But also, we've said that there's an edge if and only if the distance is less than theta. Maybe you want to say, like, people are more likely to be connected or know each other if they're close, and less likely if they're far apart. So make that a bit fuzzy. Okay? So let me show you a second implementation. I won't sort of show you all the implementations because there are lots. The second one example is an Erdős-Rényi graph. And here we forget about the geometry altogether. And in fact, there's no kind of correlations between the vertices. So we can, how do we understand vertices? Well, I'm just going to give them names, so we can do that by like a uniform distribution. And is there an edge from vertex V to vertex W? Well, it's just toss a coin. So it's independent for any pair of vertices if there's an edge between them. Right? This is the Erdős-Rényi graph. It's very hard to visualize, I think, but this is a kind of a visualization of it. Okay? So that's sort of the other extreme, where there's no geometry and the chances of edges are now random. Okay, so we'll come back to those two extremes towards the end of the talk, hopefully. But that gives you two examples of interfaces. Right, yes, let me show you another, like a more precise way we might use the interface. So I won't show you like the full graph inference problem, but we can ask, is there a horn? Let me show you that, okay? So what do? We draw 3 nodes, A, B, and C. We could do this in anything that implements the interface. And then ask, is there an edge from A to B and an edge from B to C, but not an edge from A to C? A horn for me is a triangle without a base. I just made it a bit more interesting than a triangle, so yeah. And this returns a Boolean. It's either true or false. We either get a horn or we don't. So it's a random Boolean now. So with some probability, we'll get a horn, and with some probability, we won't. So it's describing a random Boolean. Okay, and as I said, we could run this on the Erdős-Rényi thing here. It'll be, I think, 1/8 will be the probability of getting a horn. But we could also run it for the geometric things. It makes perfect sense, just using the interface. Okay, so I'll come back to that horn example a bit later as well. But let me first just have a chat at a higher level about the idea of interfaces in probabilistic programming. So we're focusing here on graph inference, but we could also look at regression, which is perhaps a even more famous kind of statistical problem. And there, we're also interested in a very similar abstract type, but it's slightly different. So now we're interested in some parameter space. Maybe it's linear regression, like in the top left, where you have the slope and the intercept as the parameters. So we've got some distribution on the slope and the intercept. And then rather than an edge relation, we have an evaluation function that, given the parameters for the function and an argument, produces a result. Perhaps some of you went to Ohad's tutorial on Monday. We've looked at these kinds of things quite a lot. For example, the quasi-Borel spaces was meant to explore these kinds of structures. Okay. So that's another kind of abstract type. It looks a little bit similar in flavor to the graph one. But there's plenty others to study, which we mentioned a bit in the paper, but I think there's still a lot of work to do. But the high-level view, I guess, is that abstract types and interfaces in probabilistic programming correspond to important statistical structures. And I guess it's a two-way street, because we can start to inform statistics by programming. Right. Okay. So let's move back to the theorem and start to explore a bit what well-behaved means. Okay, so back to graphs and exploring a bit more about the theorem. Okay, so what is a well-behaved implementation? So some of our implementations need to use hidden state to describe the structure. So that's why it's a little bit subtle. Let me step away from graphs for a second, though, and talk about probabilistic programming with sort of more basic interface to try to agree with you on what kind of structures, basic structures, we should have in probabilistic programming. So here I've got normal. Don't worry if you don't know what a normal distribution is. It's just a distribution on the real numbers. Doesn't even have to be on the real numbers. But I'm drawing A and B from normal, and then I'm doing 2A plus B to return a result. Okay? And the point is I've got 3 programs here, and they're all the same. They should all do this, they should all give the same kinds of results, but they may do slightly different things along the way. So the first one draws A and then B. The second one samples B and then A. And the third one samples C and then B and then A, but doesn't use C. Okay? So if we're thinking of maybe a Monte Carlo simulation, might actually have some state in there if it's doing something clever. So it might do actually under the hood different things for all 3 of these programs. But I hope you can agree, like intuitively, the 3 programs should give the same statistics in the end. Because if instead of normal, let's toss a coin. If I toss a coin with one hand and then a coin with the other, it doesn't matter which order I toss coins. They don't communicate. The coins don't communicate to each other. So we can reorder these things. So let's take that as a primitive, basic axiom for probabilistic programming, that at this level, program lines can be reordered. It's like a commutativity property. So, right, so this is a view of probability from a programming language perspective, but let's bring it down to a probabilistic point of view. If we think of these programs as Monte Carlo samplers, computing integrals, here K is a continuation, what happens next, then we can understand the program on the left as a double integral over A and then B, and the middle program as a double integral over B and then A. And the fact that these integrals are the same is Fubini's theorem, which says we can reorder integrals on probability distributions. It's maybe the first non-trivial theorem of probability theory. But we're going to take it not as a theorem, but as an axiom, as a synthetic description of what probability is all about. Okay. It's not just me saying this. Several other people are arguing that we should take this kind of view of, even as a mathematical view of probability. Okay, so with that in mind, we understand what's well-behaved probabilistic programming. Let me be a bit more technical for a second for anyone who wants this, and say more precisely what's going on here. We have a distributive Markov category. It's the same monoidal category with coproducts and some extra structure. Or equivalently, and what's nice is that these things are the same, an affine monoidal monad on a category with sums. And that gives us this, the monoidal thing gives us this interchange, gives us the exchange, the commutativity. And let's insist, moreover, this is, I guess, something that I haven't seen before in Markov category literature, that we know what Booleans are. We know what random Booleans are, right? They're just like coin tosses. We don't want to have unusual interpretations of basic finite probability. So I want to have strange interpretations of the type of vertices or of real numbers and stuff like that. But for Booleans and for finite types, I don't want to do anything controversial. So to fix that, we say what we call a Bernoulli-based Markov category, which says that the numerals, the finite types, just give us stochastic matrices. Okay, so that's our formal model of what a well-behaved probabilistic programming language is. Okay, so with that, we're ready to prove the theorem. Okay. And I'll prove it by example, don't worry. So let's start from this interface, and we've already seen the chance of a horn, this program here that draws A, B, and C, and then asks, is there an edge from A to B and B to C, but not from A to C. I'm going to do some manipulations to this program now, based on the equational reasoning that we've all agreed is okay for probabilistic programming. So let me copy the program. That's exactly the same program. They're definitely equal. And then let's use the data flow property to just flip the second and third lines. Okay? I said I can always do that. There's no variable dependency, so I can always do that. Okay, so these programs are equal, and that's our assumption. It's a well-behaved implementation. Then let me do alpha conversion. Hopefully everybody's happy that alpha conversion should be allowed. So I rename B and C. I swapped the names B and C. It may look like lines 2 and 3 reordered again, but no, I just swapped the names B and C. And now if I read this, it's talking about the chance of a horn where there's an edge from A to C and an edge from B to C, but no edge from A to B. So these two programs must be equal because I only used things that we all agreed were okay to do. Therefore, the probabilities of getting these two horns are equal, and we could also show that the third horn is equiprobable. In other words, this commutativity condition for probabilistic programming has given us exchangeability on this particular finite random graph. Okay? So the finite random graph that we're getting here is invariant under permuting the vertices. And this invariance is called commutativity. Okay. So this is an example of one particular property on a 3-vertex graph, but it works for any property of any finite graph. And this is the route then to programming. So to proving the theorem. So yeah, so to go from a well-behaved implementation that satisfies commutativity and just data flow, we get back a graphon by remembering that it's well known, or it's known in the graphon community, that a graphon is the same thing as an infinite sequence of finite random graphs that's exchangeable, that's what we just saw, but also satisfies two other conditions, consistency and locality. I won't show you those conditions, they're in the paper, of course, and they're also very simple to show using just program manipulations and basic equational reasoning. Okay? So from a program, we get a graphon by getting this infinite sequence of finite random graphs, and it's exchangeable, it's also consistent and local, therefore it corresponds to a graphon. To go the other way is a bit more non-trivial. For black and white graph, so if we think of a graph on as a heat map, if it's black and white, we have a simple implementation, and we saw the geometric implementation. A very similar one works for any black and white graph one. If it's grayscale, we need to use some hidden states, and that's where things become more interesting and complicated. So for constant gray, so ideally we'd like to build a distributive Markov category, right, that is Bernoulli based. So to do that for the constant gray one, we used Rado nominal sets, which various people have considered before, but not in this probabilistic context. And for arbitrary grayscale, we don't have a concrete method for building a Markov category, but we have an abstract one that uses some techniques from category theory. So I guess we're trying to build up a way of building these synthetic models of probability. So that's the theorem. I guess a high-level view is that abstract types in probabilistic programming connect to concepts in probability and statistics. And hopefully that's a two-way street where we learn things about programming and we learn things about statistics. Thanks.
Do we have any questions?
Thank you, excellent talk.
Thanks.
So one question about the Boolean. So there are some applications like in computational chemistry and the combinatorial chemistry where you want to have modern graphs, hypergraphs.
Yeah.
Could you imagine an extension of what you're doing in that direction?
Absolutely, yes. So we focused here on graphons just to keep it simple. It's complicated enough, but I don't know how easy it is. There's all kinds of other structures, not just hypergraphs. Here we are. Hierarchical graphs. Absolutely. These are the kinds of structures that should be studied. Yeah.
Can the next speaker come forward to the podium? Any other questions?
So when you did this new operation,
Yeah.
it was generating, in the example that you had, the edges were being generated as you did this. And obviously, if I was if the likelihood of an edge was inversely proportional to the number of nodes that was there, and, which would appear in many applications of generating graphs, you wouldn't get this interchangeability property. Can you speak a little bit about just like what prevents, me from, what are the conditions that are guaranteeing the interchangeability there?
Then you would need some hidden state to do this. And I guess if your hidden state gave you something that wasn't exchangeable, wasn't commutative, it wouldn't correspond to a graphon. So those are certainly interesting random graphs, but they don't correspond exactly to this familiar characterization of a graphon.
So a graphon always has these properties?
Always has these properties, exactly. Yeah.
Thank you.
Yeah.
I think we have time for one more question.
Could you explain more about the usage of the assumption about the coproduct? Is that for interpreting if the control flow or what?
Yeah, so I need a coproduct in my category. Well, I need Booleans, which I think has 1 plus 1, which is a coproduct. Okay, maybe we don't need all coproducts, but it just felt easier to say we'll have all the coproducts. Yeah. So it's an if-then-else interpretation, yeah.
Okay, let's thank Sam again. The next talk will be Inference of Probabilistic Programs with Moment Matching Gaussian Mixtures.
Okay.
And the talk will be given by Francesca Randone.
No, it's okay, I can do without. Okay.
Can we get the slides?
Should I plug and unplug? Okay. Sorry for the colors, but I don't know why they're like this. They show up right here, but they're not fundamental, so I'll just go on with my presentation. I'm Francesca Randone. I'm a PhD student at IMT School for Advanced Studies Lucca, and I'm going to present a paper which is joint work with Luca Bortolussi from University of Trieste and Emilio Incerto and Mirko Tribastone from IMT Lucca. So before starting, it's not going on. Plug and unplug. Also here it's stuck. Maybe I can just do this.
Apparently it's not transitioning.
Yeah, on my screen is going, but
Okay.
on the little screen here, no.
Do I just say that
Keep on talking for now, okay? Okay, now it should go. So thanks. As I was saying before starting, I wanted to recall quickly what a probabilistic programming language is. And that's just a programming language augmented with primitives expressing probabilistic behaviors, such as random assignments, which means I assign a variable with a probability distribution, probabilistic choice, which means I execute a subprogram with a certain probability p, or conditioning, which means I constrain a given distribution to take values in a certain range. And in our paper, we take the point of view of seeing a probabilistic program as a transformer on distributions. So you can imagine to have a prior or input distribution on your variables, for example, a standard Gaussian distribution, and your probabilistic program acts on the distribution to transform it, so that at the end of the execution, you will have a different distribution on your variables, which we call posterior or output distribution. And it's described by a probability density function f, which is highly non-trivial to compute. And just to give you an idea of this, consider a very simple toy example, just 10 lines of code, and very simple distributions involved, independent standard Gaussians. However, even starting from these simple distributions and this simple program, we get a complex output distribution, where by complex I mean that writing the PDF of this distribution is non-trivial. So we asked ourselves whether we could approximate efficiently the output distribution, or at least some moments. And of course, we're not the first one to ask this question. Actually, it's a very well-known problem called the inference problem. And actually, there's a whole bunch of literature dealing with developing efficient methods for this. And this is a non-exhaustive list, but you can see that there's really a lot of work going on, and each of these methods are tailored to some kinds of distribution, some kinds of program. Some are exact, some are approximate. And our contribution to this is to introduce a new method based on an analytical approximation, for which we provide a theoretical framework called Gaussian semantics, and also a practical implementation in a prototype tool called SOGA, Second Order Gaussian Approximator. The two distinguishing features of our approach are the ability to deal with both discrete and continuous distributions, and the fact that in the theoretical framework we provide formal guarantees on the approximation. Okay, before going into the details of our approach, let me go back to the toy example. Here I will just show the marginal, but you can imagine also working on the joint distribution. So we start with independent Gaussian distributions over x and y, and we enter this if branch with condition x greater than 0. At this point, the marginal over x is not a Gaussian anymore, but a truncated Gaussian. And that's fine. I mean, with a little bit of effort, we can still write the exact PDF of this distribution. But what about when this sum happens? Now, the marginal over x is given by the sum of a truncated Gaussian and a Gaussian. And in general, to write the PDF of this distribution, we have to compute a convolution integral. And we all know that integration is a very expensive operation to perform. So already at this point, many of the approaches that I've shown you before would resort to sampling. But we asked whether it was possible to find an approximation that allows to perform this kind of operation, so truncation, conditioning, and arithmetic operation in an efficient way that makes it easy to compute. Our answer to this question was, what about Gaussian mixtures? Just to recap quickly, a mixture is just a distribution in which you have a finite number of components, and each component comes with its own weight, which is a number between 0 and 1. And in Gaussian mixture, every component is a Gaussian distribution with its own mean and covariance matrix. And we thought that this could be a good representation because of properties of Gaussian mixtures. Namely, the fact that with a simple trick, they allow encoding both discrete and continuous distribution, because you can see a degenerate Gaussian with null covariance matrix as a delta distribution centered in the mean, and a discrete distribution is just a mixture of deltas. So you can see a discrete distribution in some way as a Gaussian mixture. But moreover, Gaussian mixtures are dense in the space of distribution when equipped with the Levy-Prohorov metric. And this means that for any distribution, you can find a Gaussian mixture which is arbitrarily closed with respect to this metric. So they're universal approximators. And finally, computing moments of transformed Gaussian mixtures is quite easy. Why? Because computing moments of transformed Gaussian is. And in this table, I show that for different operations that you can perform on Gaussian, you have theoretical results that allow you to compute exactly the moment of the transformed Gaussians and the 4 moments of the transformed Gaussian mixtures. So going back to the toy example, in the exact semantics, when we enter the if branch, we would have a truncated Gaussian as a marginal over X. But in Gaussian semantics, instead we use a Gaussian mixture, and we choose the parameters of the Gaussian mixture so that this mixture here has the same moments as the truncated Gaussian up to a certain order R. Remember that I told you that here I'm just showing the marginals, but actually we do this using the joint distribution. So what we would do in reality is using multivariate Gaussian mixtures. And this has another advantage, which is the fact that when we perform the sum, we're introducing a dependence between x and y. And using multivariate Gaussian mixtures, we can encode this dependence in the covariance matrix quite easily. Moreover, at this point, computing the sum of a Gaussian mixture and a Gaussian distribution is practically straightforward. This is the whole idea behind the Gaussian semantics, which is basically whenever a non-Gaussian distribution comes out, you just approximate it with a Gaussian mixture by moment matching a certain order of moments. So here, for example, you have a program location pi that would transform the Gaussian mixture G into a distribution D. And I hope I convinced you by showing the table before that computing the moments of D is relatively easy with respect to computing the whole PDF. But once we have the moment, we can just moment match a Gaussian mixture and keep on performing operation on Gaussian mixtures. And here the important job is done by this operator, the moment matching operator, which basically, once the moments are computed, finds a Gaussian mixture having given moments, and is parameterized by this index R that tells you, well, in which we decide how many moments we want to match. Quite a significant part of the paper is spent to define this moment matching operator. We do this in a recursive manner so that when we act on a mixture distribution, we moment match each of its components, while when we act on a distribution which is not a mixture, so in some way it's an atomic distribution, we just moment match directly the distribution. But to make a long story short, we show that it is possible to give a criterion so that this operator is well defined. And what's more important, with this well-defined operator, we are able to prove this theorem that tells us that when you moment match an increasing number of moments at each program location, the distribution yielded by the Gaussian semantics will tend to the distribution yielded by the exact semantics. And here you can see in the graph that the truncated Gaussian, the blue line, is approximated better and better by moment matching 2, 3, or 4 orders of moments. Now, until now, I've talked about moment matching any order of moments, but actually it turns out, unfortunately, that when you try to moment match 3 or more order of moments, things get complicated. Why? Because you have to solve a system like this. You don't really have to go through every equation. It's just to give an idea. So basically, you have to solve a constrained polynomial system of equations, and we didn't find a way to do this efficiently. However, when you want to moment match only 2 order of moments, this becomes extremely easy. Why? Because if you have a distribution and you want to find a Gaussian mixture having the same mean and covariance matrix, you can just take a Gaussian, and that's it. You don't have to solve any kind of system. So in the tool we present, we do exactly this. At each program location, we moment match only 2 order of moments. And so, yeah, our tool, Soga, just takes as input a script of a probabilistic program written in a certain syntax. And it executes second-order Gaussian semantics, returning posterior mean and covariance matrix. In the paper, you will find extensive experimental evaluation for our tool. Here we are comparing it for posterior mean estimation with respect to Monte Carlo Markov chain sampling in STAN, posterior quantization performed in Aqua, variational inference in Pyro, and symbolic exact execution in PSI. The corpus of benchmark is taken from these tools reference papers, and there are the benchmarks that are currently supported by our syntax. And basically, we found out that being able to deal with both discrete and continuous distribution is quite convenient, because, for example, STAN, Aqua, and variational inference only support, in a limited way, discrete distributions. While with respect to the exact symbolic approach, the main advantage we have is that even when this approach goes time out, we are able to reach a numerical answer using different level of approximations. Okay, what I shown before was about posterior mean, but what about modes? Like, mean was kind of expected since our method is moment-based, but are we able to retain information about the mode or the distribution? Turns out that we are slightly less accurate when it comes to mode, but we still perform comparatively well with respect to Pyro. And finally, in the paper, we also show 2 applications in which our method scales really well. The first class of models is given by models in which mixtures of continuous density functions and discrete probability mass appears together. And here we've compared with BLOG, which has a dedicated algorithm for this kind of distributions, and variable elimination. And we found out that with respect to program length, our tool was able to scale much better. And the second class is given by collaborative filtering, which is a model used in recommendation system, which has this form you see on the top of the slide. And here you usually impose a Gaussian prior. And because of this particular form of the model, our tool performs particularly well on this kind of model. And when compared with STAN, Aqua, and variational inference in Pyro, we found a better scaling with respect to an increasing number of variables. So to conclude, yeah, for more details, I refer you to our paper. And we also have an artifact, which has been deemed reusable, so you're invited to play with it. But we're actually working on a tool paper in which we would like to improve the stability of the results, extending a little bit the syntax to make it more usable, and also perform more like deeper sensitivity analysis. The final aim would be to integrate our method into existing probabilistic programming languages such as Pyro, but I've also heard a lot about Julia in the past few days, so I would be interested in that. And yeah, but there's a lot we can still do, like fitting higher order moments to improve the accuracy, or look into the differentiability of this particular family of semantics. And we're open to any kind of possible applications. So thank you for your attention. And yeah, that's all from me.
Can the next speaker come forward?
Hi, thanks for the great talk. You mentioned that you're working with second order approximations in your implementation, and that you can always do that with a single Gaussian. So I'm wondering if you can comment on when your implementation chooses to introduce mixtures with more components.
Yeah, as I said, okay. As I said before, the mixture part comes into play when because of the recursive definition that we give to the moment matching operator. Basically, what happens is that we represent the program as a control flow graph, and the mixture comes into play when you have if branches, for example, because for each path you will moment match the component coming from that branch, and then you put them together into a new mixture, and you keep on executing the Gaussian semantics on this new mixture. So yeah. I hope this answers your question.
I have not understood if you have an unbounded loops, how you get the distribution, which is the limit of the distribution for the iterates.
Yeah, that's a good question, but we currently don't support unbounded loops. We work with a bounded control flow graph, so that would be a very interesting extension for the future.
Okay, so
very complex, probably.
You have not solved the problem, huh?
Thanks. Can you maybe comment? Maybe there's some situations where VI performs better. I don't know. Maybe highly multimodal or high dimensional.
Yeah, like one thing we found is that at least for the implementation in Pyro, the scaling with respect to the number of variables in variational inference is less severe, like than with respect to other approaches. I think thanks to vectorization, but I'm not completely sure. So that could be one reason. But like what we found is that with variational inference, you have to also to be a bit lucky with your hyperparameters. So maybe with some hyperparameters, you can have excellent performance. With others, you don't. While with our method, you don't have to do so much tuning, let's say.
Do we have any other questions?
So when you do the experiment with Pyro, did you use auto-guide generation, or did you manually generate the guides?
No, we use mainly auto-guide, I think, except for some models for which we had to manually write the guide.
Any other questions?
Sorry, this does reminds me of something like message passing or expectation propagation. Have you compared it to something like infer.net, which underlying the vector graph and message passing?
No, I'm not really familiar with what you're mentioning. We compared with variable elimination on some models, but not which I think might be similar, but I'm not really familiar with that kind of literature, so yeah, maybe we can take this offline.
Yeah, let's thank Francesca again. Okay, the next speaker will talk about higher order Bayesian networks exactly. And the speaker is Gabriele Vanoni. showing, so it should be mirrored.
I'm sorry, one moment. Okay, do you hear me? Yes. Okay, this is joint work with Claudio Faggian from IRIF and Daniele Pautasso from Università di Torino. So a little anecdote. Before yesterday, I lost my laptop and my slides were on it, and they weren't backed up. So I did my slides again from scratch this morning. So maybe they will not be very fancy, but still. Okay, so we start from a very simple graphical model. These are Bayesian networks. This is an example of a very, very simple Bayesian network. So we have a random variable, a Boolean random variable. This is rain, where rain can be true or false, and can be true and is true with probability 0.2, is false with probability 0.8. And then we have another Boolean random variable, wet grass. And so the probability of the grass being wet depends, of course, on the fact that it has rained or not. And so the probability of the grass being wet is defined by the table there. So this is a Bayesian network. So what is a Bayesian network? In general, it is a directed acyclic graph together with some conditional probability tables which are attached to each node. And Bayesian networks describe our knowledge of a portion of the world, let's say. And what we would like to do using Bayesian networks is Bayesian inference. And so everyone knows that Bayesian inference computes the posterior distribution, so the knowledge that we have once we have some evidence, once we have observed some facts about the world. And the posterior is proportional to the likelihood multiplied by the prior, and it is normalized by the probability of the evidence. So for example, in this case, we could ask ourselves, what is the probability of rain being true given that the grass is wet? And we can compute it according to the previous formula, so using Bayes' theorem, as the probability of the grass being wet given that it has rained multiplied by the probability of rain being true, and we normalize by the probability of the grass being wet. So this is standard Bayesian statistics and standard Bayes' theorem. And so why do we use Bayesian networks? And why don't we just use standard Bayesian reasoning? So the pros of Bayesian networks is that they are very simple. So we are very constrained in the description of our model because it's a directed acyclic graph. And in particular, we can represent, using these graph and these kind of tables, in a very compact way, possibly very large probability distributions, because we don't have to express the full joint probability distribution, but we just highlight the dependencies between the random variables involved. And in particular, we have very efficient in practice algorithms to do Bayesian inference using Bayesian networks, exploiting the graph structure of the network. So is there also a downside? Yes, of course. Since it is a very simple model, maybe it is too simple. It's a first-order model, and it's not hierarchical in nature. It lacks expressiveness, the typical expressiveness of programming languages, and it lacks modularity, compositionality. So everything has to be described using this graph that can grow a lot. So for example, let us consider a case in which we have a model that depends on time. So for example, Markov chain or similar kind of models. So we can describe such a model using this notation from taken from the typical statistics books and typical statistics papers. So it's called a plate notation or a template. So we observe that we have a state which depends on the previous state, so like in a Markov chain, let's say, and we have an observation of prime which depends on the state S prime. So this is a template. This means that it can be unrolled a certain number, a finite number of times, for example, in the picture 2 times, and this is the resulting unrolling of the template. So it is a real Bayesian network. So the one on the right-hand side is an actual Bayesian network. So this is the notation people in statistics use. It's quite clear, I would say, but still it's not a formal notion. It's not properly mathematically defined. And so we ask ourselves, which is the actual semantics of the template, of the compact notation? And for example, how many random variables are involved? Because this is important. I mean, statically at compile time, using only the template, we cannot know if the template is more complex than this example. Of course, how many random variables are involved, and this is of course important because the number of random variables is the typical complexity measure used to evaluate inference algorithms in Bayesian statistics. So can we formalize all this? And so this is our contribution. Somehow, part of our contribution is in formalizing this kind of notation using tools from the programming languages theory. So we introduce, first of all, a higher order probabilistic programming language, which is able to describe complex Bayesian models, such as this template notation, but we can encode recursion inside our probabilistic programming language, so we can describe arbitrary complex models, let's say. What is the point is that the normal form of our languages are standard Bayesian networks, are first-order Bayesian networks. So we can encode in our programming language a complex model, but then if we do the rewriting until the normal form, then we obtain a standard Bayesian network. So how is that possible? This is possible because we exploit intersection types to guarantee that only meaningful programs can be written, so programs that are somehow Bayesian networks. And this is our main theorem, which says that a term T is typable if and only if it represents a Bayesian network. So, and by representing a Bayesian network, we intend that it can be rewritten to a first-order term which represents an actual Bayesian network. So our type system induces also the notational semantics, and this is fine, of course, and this is somehow standard in intersection types because intersection types are used to define the notational models. But moreover, we can read from the type derivation of our term the graph structure of the Bayesian networks that the program represents. So we can read out the structure of the graph structure, we can extract it from the type derivation, and we can also read the cost of computing the semantics and so the cost of inference. So this is our calculus. It's quite standard, I would say. You can see that we have this bank constructor, so it's a call by push value like calculus, and it has just one probabilistic constructs here, and this is a sampling from a discrete distribution. Then there are types, and these are intersection types, and so the fact that they are intersection types is clear from the fact that we have bags of types, multiset of types. So a term can be given more than one type. But the interesting thing with respect to the probabilistic aspect is that our ground types are not, for example, Booleans, but are names. N is a set of names, and these ground types represent random variables. So using intersection types, we can keep track of the different random variables that are generated during the computation. So how do we achieve our goal? Let's see this in some points, so our techniques. So first of all, non-idempotent intersection types. So these are tool that has been used in the last years to observe quantitative properties out of programs and to characterize quantitative properties. And so we use this kind of tool to keep track of random variables, copied random variables, generated random variables. But we can keep track of these random variables at compile time, let's say, statically, without executing the term. Then we use a geometry interaction, which is a technique rooted in proof theory, to do some data flow analysis on our program and to ensure that our denotational semantics is actually compositional, because this is not trivial. And moreover, this data flow analysis allows us to extract the graph structure from the type derivation. Then, as I have already said, we use a call-by-push value like lambda calculus. And this is mandatory somehow, because sometimes we want to share samples, while sometimes we want to copy the sampling primitive and actually duplicate it. So call-by-push value allows us to force and find computation, and so it allows exactly that. And finally, since we compile to Bayesian networks, our normal forms are Bayesian networks, so our normal forms are not values. And so the writing theory of our language is a bit more complicated than the usual, and we need some more sophisticated rewriting techniques to handle all the cases. So what about our denotational semantics? And this has some nice properties, I would say. First of all, it's cost aware, and it's cost aware in two ways. First, because we are able to compute the cost of inference out of the type derivation. And on the other hand, more interestingly, I think, the way in which our denotational semantics computes the probability function, the probability distribution defined by a program, is exactly as inference algorithms for Bayesian networks do. So, for example, variable elimination. So this is particularly nice because other kinds of denotational semantics instead are not so efficient in computing. And second, our denotations are factors, which are the standard way in which people in statistics represent probability distributions in inference algorithms for Bayesian networks. So we don't have an exotic semantic domain for our programs, but still we use something which is very well known from the statistics point of view, which are factors, which are a generalization of probability distributions. So to wrap up, our main contributions are a higher order programming language, which is sound and complete for Bayesian networks. This means that we can represent all Bayesian networks in our language, and moreover, all the well-typed programs are compiled to traditional Bayesian networks, but still they can contain recursion and every complex behavior. Which we have a factor-based denotational semantics, which is sensitive to the cost of inference. We have an operational semantics that rewrites possibly recursive and higher order terms to first order terms. And we have a method to extract the underlying graph structure from the possibly recursive and higher order type terms. So this is all. Thank you.
Great. Do we have any questions?
For Bayesian network, which is not on the shape of trees, my understanding is that basic inference, the time complexity of the basic inference algorithm depends on the tree width of the graph. So you mentioned about this cost-aware denotational semantics.
Yes.
Does that mean your cost-aware denotational semantics somehow compute this tree width-like parameter implicitly throughout the denotational definition or something?
Yes. The point is that when you have a variable elimination, the cost of computing the inference depends on the order in which you eliminate variables, and this order is implicitly inside the structure of the lambda term. So you could rewrite somehow the lambda term using some commutative conversions to change this order of eliminating variables. And so you would have also another kind of cost. But given a term representation, then the order of variable elimination is fixed.
Can the next speaker come forward? And do we have any other questions?
Yeah, another question about the cost awareness. So there's another aspect of complexity of inference in BayesNet's results of Dagum and Luby about like maybe NP hardness of exact results, but also showing that if certain probabilities are bounded away from 0 and 1, then you can get efficient approximation and so on. Is there any way that you've considered to sort of consider those kinds of constraints in terms of your cost analysis?
No, we didn't consider it. I mean, we didn't consider so advanced results. I think our algorithm, let's say, is just plain, let's say, variable elimination. So,
any other questions? Okay, let's thank Gabriele. Okay, Marcel Moosbrugger will explain why strong invariants are hard. And he will do this for ordinary programs and for probabilistic programs.
Just quickly mirror my screen. Yes, hello, thank you. So I'm going to talk today about polynomial invariants, both for classical programs and for probabilistic programs. And we're going to start very much in the first half with classical programs. So let's start with a very simple example. We have here a program and it takes two input integers, x and y, and then we initialize this variable set to 0. Then we have a loop, a while loop here that executes a total number of y times because we initialize the counter I to y, and then in every iteration we decrease the counter by 1, right? So in every iteration we add x to z. So after termination, z is going to be equal to x times y. So this is an intuitive justification why the result of this program is the product of x and y. But of course, as you know, if you want to prove this formally, because this program contains a loop, what we need is a loop invariant. And the loop invariant we could use for this example here to prove that after termination z is going to be equal to x times y would be this invariant, that z is equal to x times y minus ix. So this is an invariant because intuitively in every iteration z is equal to x times y, but we're still missing I many x's. And also after this loop terminates, we also know that because of the loop guard, because we terminate that I is going to be equal to 0. So if we just substitute I is equal to 0 into the loop invariant, we immediately get the post condition. So given an invariant, or given this invariant here, the verification becomes very easy, or at least automatable. And also please note that although the program here is linear, it only uses linear or affine assignments, the invariant that we used is a polynomial. And now the question is, can we find such invariants automatically? But this is still an ill-posed question, because in general there are infinitely many invariants, some of them more useful than others. But as I illustrated in the previous example, polynomial invariants are often quite useful. And so what we are focusing on is polynomial invariants, but not any polynomial invariant, but what we are looking for is the strongest polynomial invariant. So that is the set of all polynomials in program variables that are invariant for a given loop. Now you might say, okay, this is still an infinite set, but this is actually a very nice infinite set because it forms what is called an ideal. If you don't know what an ideal is, it's not so important. The important property is that every polynomial ideal has a finite basis. Quite similar to how a vector space is a collection of infinite points, but can still be described by just providing a finite basis. And for instance, for the previous example that I showed you, for the multiplication program, this single invariant that we had is actually already a basis, or a basis element of a basis with just a single element for all polynomial invariants of this loop. So the question, we now refine it, and the question now is, can we compute a basis for the strongest polynomial invariant automatically? And this has been, or this is a question that has been studied quite extensively. So for deterministic, unguarded, and affine loops, that is loops as we've seen in the previous example, just a straight line loop body and no if statements, no non-determinism, and just affine assignments. For this class of loops, this problem is known to be computable. If you put in a single if statement, your program model immediately becomes Turing complete, and the problem is undecidable or uncomputable. If we take out if statement again, but put in non-determinism, if we use affine arithmetic in the loop body, it's known to be computable. But if we use polynomial arithmetic and non-determinism, it is uncomputable. It's a very recent result. But there is a very important class of programs missing here, or very, you could say also fundamental, that is loops that are deterministic, or they don't use non-determinism, no if statements, but polynomial assignments in the loop body. And for this class of programs, computing the strongest polynomial invariant is also not known to be computable or uncomputable. And these are loops like this one. Right? We have some initialization part, and then, as I said, in the loop body, we just have no if statements, no non-determinism, but just some polynomial assignments. And you can also think of these loops as discrete time polynomial dynamical system, where the initial assignment part gives you the initial state, and the system dynamics is given by these polynomials. And as I've said, for this class of programs, for this class of loops, computing a basis for the strongest polynomial invariant is not known to be computable or uncomputable. But there are also other problems, much more problems, whose status is unknown. For instance, just reachability. Right? You're given a point and in the state space, and the question is, does this loop ever reach this target? So there are no algorithms known, but also no undecidability proofs. And the problems are believed to be very hard, and I'm going to show you that they are very hard. But there are no undecidability proofs, mainly because you cannot do a zero check in this program model. Right? So many undecidability proofs reduce from some problem where you kind of have to encode some kind of zero check within your program model for which you want to show Turing completeness or undecidability. So maybe we have to reduce our expectations a bit, and maybe we cannot show undecidability, but can we in some sense show that an algorithm is basically impossible? And what I mean by this, I'm going to make this very precise. What we show in the paper is that both of these problems, so reachability for these polynomial loops and the invariant problem, is at least as hard as the Skolem problem. So what is the Skolem problem? The Skolem problem is about linear recurrent sequences. And you all know linear recurrent sequences. Just think of the Fibonacci numbers and the recurrence defining them. So a linear recurrent sequence, you're given a recurrence equation that is linear, that relates terms of a sequence together with initial values. The question is, or the Skolem problem is, does a given linear recurrent sequence have a 0? And now also the status of this problem is unknown, whether it's decidable or undecidable. But this problem is actually as old as computer science itself, and it's connected. It has many connections to unsolved conjectures in number theory. So this is a problem where no one expects a PhD student to come up with an algorithm for it. And so what we prove in our paper is that both point-to-point reachability for polynomial loops and also computing a basis for the strongest polynomial invariant for polynomial loops, both of these problems are harder than the Skolem problem. And even more, they satisfy exactly this relation. So invariant problem is even harder than the reachability problem. I'm not going to show you the reductions we did from Skolem to reachability and from reachability to invariance, but let me just mention two short things about these reductions. So first, we reduced the Skolem problem to the reachability problem for polynomial loops. And we can also phrase the Skolem problem in a bit more computer science terms, because it's equivalent to the following. You're given a linear loop, so just the loop body is just a bunch of linear assignments, and you're also given a hyperplane in the state space. And now the question is, does this given linear loop ever reach this hyperplane? And when going from Skolem to polynomial loops, we increase the expressiveness that we allow in the loop body from linear to polynomial, but we simplify the target from a hyperplane to a point. But still, basically the expressive increase or the increase in the expressive power in the loop body takes over, and we show that reachability for polynomial loops is harder than the Skolem problem. And for the second reduction, we reduce reachability to computing the strongest polynomial invariant. And this basically means that polynomial loops are expressive enough to capture reachability within their invariance. And this is a fact that is not true for linear loops. So this was actually a very big part of our paper, the main part, but because this is a probabilistic session, let's also focus on this section here, and let's throw in some probabilities. Okay, now we have again a loop here, but now we also have probabilistic choice. In the loop body, for instance, x in every iteration either is increased by 2 with probability 1/2 or decreased by 1 also with probability 1/2. This is how this is to be read. And now for probabilistic loops, it's not so trivial what an invariant actually should be. Right? Because in general, we cannot just write down a polynomial in program variables anymore. Just because like the variables are now stochastic variables. Right? They are different for different runs of this program in general. But what does not change over different runs of programs are the moments of variables. They are the same in every run of the program, the theoretical moments. So what we could do is we could write down some properties among the moments of program variables. For instance, that these are actually invariants, that the second moment of x, so the expected value of x squared, is actually equal to the expected value of y squared. And this is an invariant for this loop. And also so are the more complicated polynomials among the first moments and second moments of x and y. So we have here expected value of x, the second moment of y squared, and also mixed moments. These are actually all invariants of this loop. And even more, these 4 polynomials in the moments now actually again form a basis for all polynomial invariants among the first 2 moments of x and y, but only among the first 2 moments of x and y. And this is a notion that we formalized in our paper as well in moment invariant ideals. And if you are asking yourself in the previous example, why only the first 2 moments? Can't we now look for, let's say, all polynomial invariants among all moments, like among all infinitely many moments? But as you know, in general, you cannot pull out the power out of an expected value operator. And this is intuitively the reason why the set of all polynomial invariants among all moments does not form an ideal and in general does not have a finite basis that we could provide. But as illustrated in the previous example, if we consider all polynomials among a fixed set of moments, for instance, moments up to order of 2 or 3 or 4, then this actually does form an ideal again, and we can do something because it has a finite basis. But please note, it's a common misconception, we do bound the moments, but we do not restrict the degree of the polynomial. So this is still an infinite set. It's an infinite set of invariants among a fixed set of moments. And these moment invariant ideals then satisfy some nice properties. So as you would expect, if you increase the order of the moments that you allow in your polynomials, you get more and more information. And it's also a proper generalization of the invariant ideal from the beginning for classical programs. And for classical programs, the moment invariant ideal of order 1 already captures all the information. Precisely because if you don't have any probabilities in your program, this is actually true. You can pull out the power operator of the expected value operator. But for probabilistic programs, the subset relation, the first subset relation is strict, and you gain strictly more information the more moments you include. And because moment invariant ideals are a generalization of classical invariant ideals, we immediately inherit all the hardness results. Right? So if we have a single if statement in your loop body, you're uncomputable. But also this new hardness result that we showed for classical programs, if you have polynomial arithmetic and probabilistic choice, you are immediately Skolem hard. What is not so trivial are computability results, right? For classical programs, the problem was computable if you only use linear arithmetic, but now we have also more constructs here. We have probabilistic choice. We may want to draw from distributions. So what can we do here? For instance, what about this loop here? We draw from Bernoulli distributions, from normal distributions. We have probabilistic choice. Also some form of if statements. And actually, for this kind of loops, we can compute the moment invariant ideals. And we have a tool and an algorithm, Polar, that can compute these things. And we can also characterize syntactically the loops for which this is possible. So, for instance, you might now expect why we can only support affine arithmetic and some form of polynomial arithmetic. We can support some if statements, but only over variables with finite support. For instance, here this if statements doesn't break computability because C1 and C2 are drawn from Bernoulli are only 0 or 1. Then there are two other constraints. And if your program falls into this setting, Polar guarantees that it can compute any moment invariant ideal of any order. And maybe as a side note, this is actually where we started the investigations for these papers, also the hardness results at the beginning, because we had this tool and this algorithm already and this notion of moment invariant ideal, and also these restrictions here. And we were wondering, can we drop these restrictions or can we relax them? And for the last 3 points here, with a bit of effort, you can see that this is not possible to drop them, but the first one was puzzling us. And then we went down a whole rabbit hole and discovered that there is still some very much unsolved problems for classical programs that then would have implication on our work here, and that's how we ended up tackling these problems. So to conclude, for classical programs, invariants are necessary to automatically verify program properties. The strongest polynomial invariant is possible to compute or is known already to be computable for affine loops. But for polynomial loops and polynomial dynamical system, this problem was very much wide open, and also the reachability problem for these loops. And we showed that both of these problems are Skolem hard, and they satisfy actually this relation. For probabilistic loops, invariant ideals from the classical programs can very nicely be generalized to moment invariant ideals. And we also have a tool and an algorithm that compute it. Thank you.
Do we have questions? Yeah.
So for this reduction from Skolem to point-to-point to invariant generation, does this just say that if Skolem is undecidable, then so are the other two, or is it also making a complexity theoretic claim?
It's also complexity theoretic. Yeah.
So it's a polynomial time reduction?
Yes. Yeah.
Okay, so then whatever the complexity of the first is.
Yeah, yeah, yes.
Thanks a lot for nice talk. It's just some naive questions. So your first example, even though it's a polynomial, it's multilinear. So suppose I focus on the multilinear invariant. Does that make things a lot easier?
In the invariant, I think it does. Yeah, I'm not. So everything becomes easier if you focus on the linear invariance. It's a very detailed observation. For those who don't know, because x and y are also just inputs, right? They don't change. So in this example, you might be able to use more simpler techniques because of this thing. But in general, for polynomial loops and polynomial invariants, yeah, we tackled this case. This is just by coincidence that this example is so simple, but good observation.
So you were talking about how for probabilistic programs, how the sequence of increasingly high order moments are strictly nested, but and in some cases probability distributions are not even determined by the full set of moments if they grow too quickly. But in cases where they are, or maybe even where a finite number of moments determines the entire probability distribution, are there special cases with sort of this flavor in which you know that things are not as hard as possible, sort of depending on constraints on the moments?
What was the last part? Not as
well,
hard as possible?
so if you know that the moments are especially nicely behaved or maybe determined by low order ones only, do you know that in those cases maybe you get positive results?
Yes, that might still be possible, and we investigated this part as well. Let me just go back to this slide. Where was it? Yes, here. This increasing chain, you mean? So we don't need the distributions to be determined by the moments. We just need the moment to exist. But yes, if you know some relationships among the higher moments, for instance, that the first two moments already specify the whole distribution, and you can basically automatically derive higher moments from the lower moments, then you could exploit these facts by adding this. Yeah.
So I think this is a pretty naive question, but in the polar, when you were talking about what polar can handle, in the case where you don't happen to use any randomness in your program, how do the guards here differ from the uncomputable deterministic guarded affine setting? What does finite support mean in that setting, and why can't I just compute a Boolean and put it as the guard to the if statement?
Excellent question. It's very much not a naive question. So the finite means that over the whole execution of this program, the variables that you use in the guard only take finitely many values. If you don't have any probabilities here, the only thing you could do is, for instance, set this to true, and then maybe in the if statement again to false, and you could do like a switch things. So
and that's because there are no operations that create Booleans other than the constants and the Bernoulli.
Yeah, exactly. Yeah. So the only thing you could do is like do case distinctions that run in a periodic fashion, basically, and then you could, in theory, also remove this again from the program by unrolling.
Any other questions? Okay, I have a question. Since you go from affine to polynomial, one might naively expect that you can do the reduction with Diophantine equations. Can you give some intuition why that doesn't work?
Oh, I know that we tried that. Of course, it's a very first approach. We're going to polynomial. There must be some Diophantine equations that are undecidable problems. We can't really use it. I don't remember now on top of my head why it didn't work, but we tried it and it was just impossible. Yeah.
Do you think you can give a reduction the other way to Scholem so that you have a ironclad argument for why you were not able to do the Diophantine reduction?
Yeah, no, I don't think so. Actually, this is a nice point. The problem could still be undecidable. This is basically just a justification that looking for an algorithm is probably not worthwhile your time. And actually, maybe if you let me, I mentioned this. So for moment invariant ideals, using probabilities, we have this Scholem hardness result, but a very loose conjecture for me would be that it's still undecidable computing moment invariant ideals. And interestingly, there are undecidability proofs that rely on non-determinism, and if you replace them with uniform probabilistic choice, the proof still goes through. But for moment invariant ideals, there is one proof from last year that use non-determinism. If you replace it by probabilistic choice, it doesn't go through anymore. There is a discussion in the paper if you want some open problem to work on. Yeah.
Okay, let's thank the speaker again. So I have an announcement for lunch. So if
No, I think it's working. They gave me the signal. Yeah. Should be okay.
All right, then let's get started. Welcome to the session on weak memory and concurrent separation logic. First up, we have Andreas presenting how hard is weak memory testing.
All right. Can you hear me? Is this working? Yeah. Okay, thanks for the introduction and welcome to my talk. This is a somewhat technical paper, but I will try to keep everything high level. So this is joint work with Soham Chakraborty, Krishna Shankaranarayana, and Umang Mathur. In this paper, we're asking how hard is weak memory testing. So the motivation, of course, is concurrency, which is now all over the place, from your pocket or your wrist to the cloud. We have communicating entities that compute on shared data. And from a verification point of view, we ask questions like, is my program correct? Does it have certain behaviors in a given concurrent setting? And this very often boils down to just enumerating all possible behaviors of a program and testing for the properties we care about. Of course, this being a weak memory session, we know that not all concurrency is the same, but just to bring everyone on the same page, I'll go through the standard store buffer example. So let's say we have a program like the one on the left, 2 threads running in parallel. The left thread writes to y, and then it reads from x. The second thread does the opposite. It reads from x and it writes to y. Maybe I can even do these fancy things. Good. And now under the standard view, the sequentially consistent view of concurrency, if you ask the question, well, can the 2 reads down here read the initial values of 0? Well, the answer is no. One very simple way to argue about it is to say, let's say the read on the left executes before the read on the right. Well, at this point, the write on y has taken place, so this read is deemed to see a value 1. Right? But actually, this behavior is fairly easy to get in many concurrent settings, concurrent environments, and that's because threads, of course, don't communicate directly through shared memory. There are caches and buffer hierarchies. So in the TSO, so-called memory model, every thread is equipped with a buffer, and every write before going to the shared memory stays in the buffer for a while. And now we can indeed observe this behavior by an execution that, say, first the left thread executes, it writes 1 to y, but now this kind of stays hidden in its own buffer. The right thread goes through, it executes x equals 1. Again, this write stays on the buffer. And now each read will, of course, see the initial values. So this is just to show that the type of behaviors that a concurrent program can have very much depends on the intricacies of the underlying communicating architecture. Right? And well, we like to take this formal, so we would like to have formal specifications of all the intricacies that can arise, and that's what gives rise to memory models, right? So these are formal specifications of all possible communication patterns that can take place in the account for buffering, caching, out-of-order execution, speculative execution, other compiler optimizations, and so on. And what you have in common in all these cases is that you have some sort of weak data consistency. So different processes in the system have a different view of the state of the system, in a sense. So in this work, we look at a bunch of memory models, standard SC, TSO, and PSO. The release acquired and relaxed fragments of C11, an extension of the relaxed fragment with a common PRF acyclicity axiom, as well as 3 fairly common causal consistency models. And without going into details, I mean, these memory models can be defined in different ways. One common view is through axiomatic semantics. So here, every program execution is represented as a graph on the right. Formally, it's going to be a triplet, we have actually 4 elements here. We have a set of events. So for example, this is an event. It's a node in my graph. Some thread is writing 2 to y. PO is the program order, so this is the total order on how events in the same thread execute. And we have a reads from relation. It tells us for every read what write it observes, where did it obtain its value from. And also a modification order, which basically gives us a total order on the total order in which the writes from the same location kind of arrived at the system. Right. So we put this all together and get an execution. And now different memory models impose different axioms that these kind of executions need to satisfy so that they can formally arise in the concurrent setting that is kind of formalized by the memory model. Right. So a bit more rigorously, we say that if we have an execution X and a memory model M, and this execution X satisfies all the axioms of M, then we say that X is consistent in M. And we also have some notation to denote this. And using this notion, it's also fairly common to order memory models in terms of how weak or strong they are. So we will say that for two memory models, M1 and M2, M2 is weaker than M1. And again, we have this notation up here to denote that if you take an execution and you know that it's consistent in M1, well, it's also going to be consistent in M2. So M2 allows more executions, more behaviors than M1. For example, you can prove that SC is stronger than TSO, it's stronger than release acquire, which is also stronger than causal consistency and relaxed, and the latter two are incomparable. So each one allows behaviors that the other excludes. And now, where does the testing problem? Okay. So I have some examples of executions just to familiarize ourselves with this graphical notation, though I'm not going to go into details. So this is our store buffer example from earlier. This is an execution that is consistent in TSO. It's not consistent in SC, as we argued about. Here's a more complex execution. It's consistent in causal convergence, but not in TSO. This is a release acquire consistent execution. And if you're looking at these for the first time and you're tempted to think of execution graphs as POM sets, that's not really the case. You can already see some cycles arising here. So reasoning about these execution graphs becomes a bit tricky. And then there are a bunch of others. In this case, you have an execution that is consistent in some memory model that is fairly weak, but not in others. Details don't really matter. And now, what's the testing setting I'm considering? Well, very often, when you have a memory model, like a candidate memory model in mind, and you want to now implement it, you want to know whether your implementation is correct with respect to your reference memory model. Well, one way to gain confidence in that is by running tests, so-called litmus tests. These are small programs that will exercise different behaviors. Now on the implementation side, so you will execute each of them a bunch of times. You will observe how they executed, and then each execution you will kind of map it back to your memory model and ask the question, is this execution now in alignment with my memory model, or am I observing something that I shouldn't be observing? That probably means that my implementation allows for things that it shouldn't really. Now, of course, very often the story is written backwards, so we have the implementation, and now we're trying to wrap a memory model around it. But I mean, this testing loop is pretty much the same here. Testing also arises in automated verification, model checking, and dynamic analysis. Basically, the idea here is that, well, I'm looking at an execution of my program that leads me, say, to a bad state, to some assertion violation. I'm asking the question, well, could this execution arise in the given memory model? If that's the case, then I'm looking at a witness of a violation. I have to fix my program. But what this testing environment now has in common in all these cases, well, you're always asking the question, is my observed behavior of the program in alignment with the memory model? And by observed here, I mean that you only observe how your program executed. You don't observe all the how messages were exchanged underneath. So in our setting, you don't have access to the reads from relation and the modification order. So a bit more rigorously, the problem we're looking at is now I'm giving you an abstract execution, this X bar. It's missing an RF and NMO. And I'm asking you, and a memory model M, and I'm asking you whether you can come up with a reads from relation and a modification order that would now explain this execution. It would explain how this observed execution of the threads actually occurred within the memory model, right? And pictorially, well, your input looks like this, and your output should look like this. So you infer these blue and red edges that make your abstract execution a concrete one. And I guess this is one of the most basic and fundamental kind of computational problems you can ask in the context of weak memory. And this being a computational problem, you probably also care to solve it efficiently. So what do we know about this problem? So in the case of sequential consistency, we have good and bad results. So we know that the problem is NP-complete already when you just have 3 threads, or even when you just have 1 memory location. But we also know that the problem admits parameterization. So when you fix both, you actually obtain a polynomial time output. So when each of them alone is bounded, it's a hard problem. When you bound both, it's an easy problem in a sense. Now, what happens when you go to shared memory? Well, the hardness results on this side, it's fairly easy to generalize. There are many works that study different weak memory models and prove this kind of hardness. But we don't really know what happens in this case when you bound these 2 parameters of your inputs. And you might also try to extend techniques from SC down here, but actually you will soon fail. It's the standard way of proving this positive result up here doesn't seem to extend to most weak memory models. So this is the task we challenged ourselves with in this work. And we actually prove a surprising and deep hardness result that is fairly stronger than what was known before. In particular, testing is NP-hard in any of these memory models. And even for abstract executions where you have a bounded number of threads simultaneously with bounded number of memory locations and even values read and written by the threads. So if you've worked in this setting a bit, this is fairly surprising. It was quite surprising to us, and it took us some time to arrive at it. As I said, I won't go into many details. Just in high level, we prove this by reduction from a problem known as monotone 1 in 3 SAT. So here you're given a 3 SAT formula where every clause is positive, so you only have positive literals. But now the catch is that you can only turn every clause to true by turning only 1 literal to true, as opposed to at least 1, which is the standard SAT problem. The proof is fairly technical, and it seemed that we needed to have it technical, so we have very complex-looking gadgets like this one, and I mean, we have a bunch of these, and then we have to connect them in a certain way so that hardness arises in a provable way. I'm not going to go into details, but just to say that it's not a standard one-page proof of NP hardness. It's quite difficult. At least it was for us. Now, this difficulty also is kind of unpleasant because, I mean, we would like to have kind of proofs that are intuitive and maybe generalized to other models. And I wouldn't hope anyone to actually generalize this in any, easy or quick way. But fortunately, the results that we have are actually fairly stronger than what I stated 2 slides ago. In fact, for any memory model M, even the ones that you might invent tomorrow, if you can sandwich it between causal convergence on the one side and causal consistency on the other, or causal memory on one side and causal consistency on the other, then you're suffering an intractable testing problem. So instead of actually looking at the proofs and generalizing them, you might as well try to prove this kind of inclusion. Now, that being said, for some memory models, bounding testing is actually in P, mostly by actually extending the techniques we have for SC. And if you care about the big picture, this is what we prove. So SC, TSO, PSO, and relaxed are all in P. But then these other memory models in here have intractable testing. And the thick arrows are these range results. So any memory model that falls on these arrows will also inherit the hardness. And I guess with this, I will conclude. And I'll be happy to take questions. Thank you.
So, questions?
Hi, thanks for the talk. Very interesting. Was there anything that you ran into that was kind of common between all of these models in the NP hard slice that was just the real sticking point, like the thing that made this quite so difficult that you wish you could get rid of?
Yeah, that's a very insightful question. So people who are familiar with this landscape will probably realize that all these models in the hard region are non-multi-copy atomic. And that might be something to investigate further. It's actually a question that one can make concrete and study, and it's planned for the future. I cannot make a comment, that non-multi-copy atomic models will all suffer this right now. But it's a very appealing to kind of go after such a statement.
Thanks.
Any other questions?
Hi, this is very interesting. I was just curious. What are the implications of these results for things like, litmus tests and things like that, if you want to test them?
Well, this tells you that you probably should turn into heuristics, or at least have some further semantic bounding that is not just based on number of threads and number of memory locations like you normally have for SC. So you have to think a bit more and maybe get some application-specific information in mind when you design algorithms for testing.
The number of concurrent writes can be a parameter to the same address?
Yeah, concurrent in terms of PRF, you mean?
If you don't have then any of them, then maybe the problem is easier.
No, the thing is that here we have a bound. Well, at least, if you have none of them, then probably the problem is easier. Maybe there is some also robustness answer there. But just by bounding them, you won't get anything because we have a bounded number of threads anyway. So this also bounds the number of, yeah.
Do you have any questions online?
So you briefly flashed this very impressive gadget. How
Impressive
did you
or intimidating?
How do you come up with those? Do you have to scratch your head, or can you somehow compile to something and then compose?
Unfortunately, this was a lot by trial and error, and from my.
I'd like to add that I had nightmares.
I'm sure the ACM can afford counseling for that.
And there were a few failed attempts before that. In a way, this was also my journey of understanding weak memory. So, I arrived at this. Now, do I understand it better than before?
Oh, there's an online question, if that's okay. A naive question. The interesting examples that let us find bugs and stuff, what number of threads and locations do they actually use in practice? Is it important to scale up to k equals 15, 100, 3?
Yeah, that's very interesting. I think many of the litmus tests actually have a small number of threads. And here we did not really want to come up with the smallest number of threads that we would see hardness in. I think that's a very difficult question. But we do use something like 25 threads and 30 memory locations. So, I don't know whether hardness persists, say, with 5 threads. I also don't want to think about it anymore.
Hi. So you said at the beginning that for this problem you assume you don't have RF and CO. So what happens if you have a partial RF or CO? Does that change some of these results if some of those are fixed by your litmus test, for example?
Well, if it's only partial, then I guess it depends on how partial it is. But what we do know is that if you have a full RF, that's also a very relevant setting, then actually this is the complexity landscape. And it's quite intriguing to look at. So this is the so-called read-from testing, where your RF is part of your input. And here, actually, all the hard models have a very easy RF testing case. The situation is completely reversed because all the models that have actually hard testing in the general case, easy testing in the general case, which is NP, have actually an NP hard testing for the RF case. So this is also worth investigating even further. Now, the sharp-eyed crowd will also see that this separating line is actually separating models that are multi-copy atomic from those that are not. So one should study this further.
one last question. Yeah.
Cheers. A lot of litmus tests that people use in practice have not just not very many threads and not very many locations, but not very many actions per location. Does anything change if you bound that?
I mean, if you bound that also, then theoretically you have a bounded input. I mean, what can range? If you have bounded locations, threads, and actions per location, then it's just a kind of a constant size input somehow.
You might only bound that.
Oh, only that.
I don't know how interesting it would be.
Well, that's already hard for SC. That's already hard for SC.
Thank you very much. Let's thank the speaker again.
All right, thank you.
Sorry, just quickly, can I also ask people to kind of defragment a little bit? So if you have a seat that's open next to you, please just start scooting down because we have a lot of people coming in. And it'll be much easier if they can just sit on the edge. Thank you so much.
Somewhere in your pants, not inside the pocket, like you need to hang this. Can I hang it in the pocket? Yeah, it can be locked, but not inside this fine. Yep. Then this, do not tap this, never. Then this.
Thank you. This is wonderful.
Fine.
I mean, that's what it is.
Okay. Yeah.
Yeah, do you mind scooting over just so, so it's easier
All right,
for somebody
all
to
set?
just come in. sit on the
I know,
edge.
it's not mirrored. That's
Then
annoying.
let's begin.
Oh, move this out the way.
Next up.
Do you want me to leave the running time?
Excuse me, we're about to start. Next up will be an axiomatic basis for computer programming on the relaxed ARM-A architecture, and Angus and Zongyun will present.
Thank you. So, yeah, we're going to talk about a technique for reasoning about programs in very relaxed settings. So we want to be able to do this because, of course, all of our modern hardware architectures, many of our modern programming languages exhibit weak behavior. And sorry, in particular, we focus on the sort of very relaxed ARM-A user mode setting. And the good news is we do have an authoritative model for the authoritative memory model, for user mode ARM-A. The challenge really is we want to be able to do our reasoning in some sort of a computational way. Whole program reasoning can be very challenging to scale. So if we want to reason about large programs, we want to be able to do it bit by bit. And the ARM-A model is extremely global, which makes that quite challenging. So to start just by quickly looking at the kind of shape that can make this reasoning difficult, this is the load buffering example. It's sort of dual to the store buffering example we saw in the last talk. We have a pair of memory addresses, x and y, which are both initially 0. And we have two threads, each is going to read from one of those locations and write to the other location. Write a 1 to the other location. And perhaps surprisingly, the ARM specification allows for the execution where both threads read a 1. To see why this is an issue, I want to briefly look at what sort of properties we expect to have in a compositional reasoning tool. So there's lots of things you might want, but at a bare minimum, we want some ability to take the sort of reasoning resources that we have at a program point and pass them through to the next program point and continue using them to reason on the same thread. In separation logic, this is largely captured by the frame rule, but there's variance. And we also want some ability to pass resources from a store to a load that reads from that store. There's many different mechanisms you can use for this, but you need something or other because you want to be able to take the synchronization that your program does operationally and reflect it logically. So what's the issue? Well, if we have both of these two properties, and we look at the load buffering example again, we can see that if we use the first property to pass resources down the PO edges at the sides, the program order edges at the sides, and the second property to pass resources along the RF edges going through the middle, we've got a cycle that we can pass resources around. In the program logic setting, this is enough to synthesize resources out of thin air, and we get into consistency immediately. So a simple approach seems challenging, or maybe even inconsistent. It's worth taking a step back and looking at why can't we just take the models that I mentioned that we have and instantiate existing reasoning tools, like perhaps Iris, with them. Well, there's a few different presentations of the ARM-A model. We have operational models. They are naturally operational. It should, in principle, be easy to instantiate Iris with their operational semantics. But these models are quite weird. They explicitly model the speculation that the architecture, that the hardware does, and they also include things like instruction rewinding. The notion of a program point isn't even well defined in these settings. It's not clear how you reason about these manually at all. We have promising models. These are also fairly operational, and they've been used to build logics before. The challenge with promising models is if your weak memory setting allows for load buffering, your promising model requires a certification step. These potentially require reasoning about arbitrarily much future execution. Again, this is very tricky, and we want to avoid it if we can. And so that leaves us with the axiomatic models. So to give a very brief summary of how these work, we execute all of our threads sort of in program order, building up a set of memory events that those threads carry out. We have a collection of, we work out sort of how they're related to one another, and then we check that there exists some ordering relation called OB on ARM, happens before in some other settings, that satisfies various properties, and importantly is acyclic. So these models they're relatively succinct. They seem like they should be straightforward to formalize, but they're not remotely operational, which can be challenging for a compositional reasoning tool. Thing has stopped advancing. OK, good. So these models are extremely global because this consistency check that OB is acyclic happens at the end of program execution. That's really annoying because lots of the information about what program behavior is allowed is only really available in this consistency check. And if we want to do compositional reasoning, we want to have that information while reasoning about only partial programs, not full executions. We can't straightforwardly just move the consistency check up and do it on partial programs because an execution that looks consistent can be made inconsistent by later events. It's very difficult to see how to sort of pre-do this in a consistent way. So to resolve this issue, we look at the axiomatic semantics from a slightly different direction, and we see that we can permute the order of the sort of check that the memory event graph is consistent and the check that it corresponds to program behavior. This gives us the OPEX semantics, which is novel, which begins by guessing a consistent whole program memory event graph before doing any execution, and then incrementally checks that that graph corresponds to program behavior. So to give a brief flavor of what this looks like sort of formally, we have two major steps of the operational semantics. Initialization. At the beginning of time, we guess a memory event graph G. This is for whole program memory event graph. It's required to be consistent with the axiomatic model, but at this point doesn't necessarily correspond to program behavior in any way. And we initially have a fulfilled event set, which is empty. Then as we execute the program, so say for an example, we execute a load instruction. We check that the graph contains all the appropriate events. So in this case, a read to the same memory address of some value, and that they haven't yet been fulfilled, and we mark them as fulfilled. If the graph, which was arbitrary, doesn't contain the events that we needed to contain to execute some instruction, those configurations are just stuck. But we don't consider this to be a failure state. We just discard those executions. I should note there's lots and lots of state missing from this configuration required to track all of the graph structure that needs to be there. This is a gross simplification. So at this point, we have in hand a semantics which, while it's not really executable, is certainly operational enough to instantiate Iris with. And I'll hand over to Zongyuan to explain what the program logic that we get by doing that looks like.
So on top of the OPEX semantics, we build a program logic using Iris. The logic is called Excel, and they support thread modular reasoning about the ARM's memory event graphs. And to do that soundly, we need to introduce a few new Iris assertions. So firstly, we have this register point to assertion, which means that the register R has value V, and the value comes from a memory event A. And secondly, we have a tie to assertion, which essentially tie the resource P to a memory event. And intuitively, it allows us to detach the resource P from the program point. So these two assertions are very important for sound resource parsing along program order. We also want modular reasoning. So that's why we introduced our own whole triples that is indexed by an additional per location protocol. So this protocol phi allows us to transfer resources between threads. So when we're writing to a location, we give away resources, and when we're reading, we obtain them. to see how XL works, let's have a look at the message passing example. So in this variant, we have two threads. On the left, we first write 42 to the data location, and we set the flag with a release write. So the release write here induces an OB ordering between these two store instructions. And similarly, on the right-hand side, we first read from the flag, save the value to R1, and we use R1 to compute the address of the second load instruction. This is so-called address dependency in ARM, which also induces OB ordering. So the simplification I want to prove over this program is that on the reader side, eventually, if the value we read from the flag is 1, then the value of the data must be 42. And to do this in a thread modular way, we first need to set up the prolocation protocol phi. And we say the protocol phi at data location is saying that the value of the data is either the initial value 0 or the value 42. And the protocol at the flag is saying that it's either the initial write or the release write that is PO ordered after the write of data with 42. With this protocol in hand, we can reason about this example. On the left, remember how the OPEC semantics is working is essentially checking if the program behaviors matches the graph we guessed at the beginning. So here we have a store instruction, which means there must be a write event in the memory graph. In addition, because we are writing to this data, so we have to prove that the protocol is satisfied, and can be done by picking the write disjunct out of protocol. Similarly, the release write, after the release write, we know that there's an event B, which is PO ordered after the first event A, and we can also discharge the propagation by picking the write disjunct. On the right, we first read from the flag, and we save the value to R1 register. After that, we know there must be a read event with value V flag. We can also update the register point to predicates with V flag at C. Here, at C meaning that this value V flags come from the event C. In addition, because we're reading from the flag, we obtain the protocol resource. But here we have to attach the 5 flag to the event C because otherwise it won't be unsound. And next, after reading the data, we do same things. We update the registers, and we obtain the resource file of data, and we attach that to D. And here, because of the address dependency between C and D, we know that they are ordered. So that allows us to actually pass resource from event C to the event D. By doing so, we have collected all the information we want to know about this graph, and by some quite straightforward graph reasoning, we can conclude a post condition. And XL is also sound. But proving this is sound is quite challenging. Essentially, this is because there's a tension between two things. First is that we want to reason about program in the program order, but the induction principle provided by the ARM model is along OB. We formulated XL's soundness as the adequacy theorem. And this adequacy theorem, the statement is quite close to the standard Aries adequacy, but we claim that the proof is novel. We have to resolve the incapability issue mentioned by Angus by stratification. So essentially, we split what we usually do in the Aries adequacy into 2 parts, and we do that separately in 2 traversals over the program executions. In conclusion, XL is a very expressive program logic for user mode ARM memory model, and it's fully maximized in Coq using the Aries framework. We have some limitations. First, we're lacking some support for the coherence axioms, and we're missing some abstraction that can make our logic easier to use. But we do hope that our approach here will generalize, in the sense that first, the OPEC semantics can be adapted for other axiomatic memory models, and the idea of tying resources to events will allow sound reasoning of other very relaxed memory models, such as RISC-V. And one more thing, a little advertisement. If you want to see some interesting robots, here's this event tonight. You can check out. It's very close. That's all. Thank you.
Thank you. Any questions?
Thanks for the talk. In this model, did you consider any event structure-based model for reasoning about these PORF cycles while developing this logic?
So I'm more unfamiliar with the event structure-based weak memory models than I should be. I'm not sure offhand if there's an equivalent one known for ARM-A. My inclination is that there isn't, which would sort of be a problem for us. The problem though is to some extent inherently logical, right? If you want to be able to pass resources along both of these kinds of edge, and if you allow it, it's inconsistent in the logic. It's not. We present it in the axiomatic model because that's where it's like most clean. It's an inherent problem with the reasoning principles that you want to have in your compositional reasoning tool, which we have to sort of make changes in the logic as well. Not just in the model. Sorry, we can't avoid it just by picking a clever model. We have to make changes in the logic to prevent this inconsistency.
Okay, thank you.
We have some discussion in the Discord, but also a question. So check out the Discord thread if you want to see the discussion. But the question is, it's nice when a memory model has both an axiomatic and an operational description. Could you do this for your model?
So to be clear, we don't, well, the model we're using is the standard ARM user mode model, for which there are already axiomatic and operational and promising models, which have been proven equivalent. The OPAX semantics is reasonably obviously equivalent to the existing axiomatic model. So it's not really a new model in that sense, and the existing models are already known and equivalent.
In the grammar you showed for the iris assertions, you had this annotation phi at the Hoare trippers for the protocols. Yep. Often in iris we instead make, like, instead of annotating this syntactically, it can be very useful to make this dynamic. Like iris invariants are not annotated at the Hoare tripper. You can dynamically allocate them anytime. Is there a reason why you didn't do it that way, or is that something you plan to look into? Or well, I was just wondering what's up with that.
So I think it's not very clear to us that using invariant in this weak memory settings is sound. So in particular, if you want to get some resource out of the invariant, it had to be guarded by some stuff like the tied to assertion I have shown to you. Otherwise, you cannot just naively use that resource from the invariant and pass that along PO.
Right, but this is about hiding, right? Like when I do reasoning in a program logic, I might want to have a higher order function that returns a closure, and I want to hide the invariance that the closure relies on, and therefore I don't want to have annotations at my Hoare tripper. So if I imagine a language in this memory model that wants to do hiding, I wouldn't want these annotations. I don't see how that would be related to getting resources in or out. That seems orthogonal.
So it's not clear, at least to me, that you can do it's not immediately obvious how you can build protocol-like reasoning out of just invariants in a weak memory setting. If you want to do this sort of protocol resource transfer, just using invariants.
I'm not saying just using invariants. I'm saying make it dynamically allocated.
Sure.
Have a view shift which you pick a protocol and then you have an assertion which says this is my protocol instead of having it syntactically annotated. Like IGPS still has hard-coded protocols, but they're dynamically allocated, right?
I suspect, but have not proven, that you can give a single static protocol that sort of uses Go state to keep track of a dynamically changing protocol. I think you can do this. I think it's very similar to the way you'd expect it to work with IGPS. We haven't proven it in this setting, but I don't see any reason why it wouldn't work.
Okay, thanks.
Do we have time for another question?
Yeah, one more question. Thank you. About the OPAX semantics, could you clarify why it's
important to guess the whole graph ahead of time and then progressively work into it, as opposed to gradually building the graph?
So there are a couple of different things you can do, and they work somewhat similarly. There have been pencil and paper versions of this logic where you guess sort of incremental chunks of the graph as you go along. I think it's basically equivalent, but harder to write down. It's important that you have sort of enough of the graph to keep it consistent at all times, which might be, even if you do this incrementally, you'll often need to guess events a long way in the future. And once you're doing that, it didn't seem, it seemed like you might as well guess the whole thing at once if you're going to be guessing unknown things and having to discard executions anyway. You might have to do that if you want to reason about infinite executions, but there are fun other problems with infinite executions in these settings anyway, so we sidestep that a little bit.
All right, let's thank the speakers again. All right, so next up, Leo will present Trillium, a concurrent and distributed separation logic for intentional refinement.
And this must be good to the right side.
Okay, thank you. So like all the talks in this session, this is a joint work with the wonderful people from Oath University. So one of the main goals of Trillium is to prove termination of concurrent programs. So we'll explain how it works on this simple example. So if you start at the bottom in the entry point of the program, we allocate a new reference B, which contains a Boolean. And then we spawn two threads, yes and no. And each want to flip this bit k times. But the difficulty is that they don't want to flip it in any ways. So if you look at the yes thread using a compare and swap, it tries to flip it from true to false using a compare and swap. If it succeeds, which means that the Boolean was true, then it decrements its counter, otherwise it loops back. And no tries to do the opposite, or flipping from false to true. Now, does this program terminate? The answer is no. Because, of course, for one thread to make progress in any state, at any state, only one thread can make progress, depending on the value of B. So if B is true, yes can make progress, but no is stuck waiting for yes to make progress. So if the scheduler is kind of mean to us, and all these schedules no, then no progress will be made, and the program clearly doesn't terminate. Of course, in practice, it does terminate if you implemented this, because schedulers are what we call fair, which means that they kind of run all the threads that are able to run. So now the question becomes, does this program fairly terminate? Intuitively, it does, because like I said, at each state, one of the two threads can make progress. And since the scheduler is fair, if the right thread runs, it will make progress, and if the other thread runs, it will not help, but it will not halt either. So in the end, the progress is made and the program terminates. But how do we prove this kind of formally? So here, our approach is to have a program logic that can guarantee that a concurrent program fairly terminates. And there are already such logics. One prominent example is Tada Live. But there is no kind of free lunch in life. And while it has very strong guarantees, it's kind of less expressive than logics that only handle safety properties. For example, it does not have higher order Go states. It doesn't have impredicative invariance, which means that you can nest invariants inside of each other and so on. So in this work, we kind of try to take the other direction. We start from a logic which is very expressive, but can only handle safety. In that case, Iris, of course. And then we try to see how we can prove fair termination of concurrent programs. Now there is a slight problem, which is that Iris kind of is based on step indexing, which kind of fundamentally says that it cannot only prove safety properties. And of course, termination is a liveness property. So we cannot kind of attack the problem head on, and we have to take kind of a roundabout roads. And I would like to note that this is not an artifact of Iris in particular, because the only way we know today how to have impredicative invariance is to use step indexing. So this is not just for Iris, but any logic such as Iris. So what we propose here is a logic called Trillium. And its purpose is to build a refinement between any program and any label transition system M that the user chooses. Now, there are two reasons why someone would do this. The first one is that once you have this refinement between the model M and the program, you can transport properties from the model to the program. So here, in that case, it will be fair termination. And also, of course, it's well known that sometimes refinement is a very good way to specify in a very intentional way the behavior of a program in a way that kind of usual Hall triples cannot really handle. So if you go back to our program, we can use the model on the right. So here the state is a pair. On the first component, it's an integer, which corresponds to the value of the counter of the no thread. And the second component is a Boolean, which corresponds to the value of B in the program. And once you know the value of B and you know the value of M, you can basically recover the value of N, the counter of the yes thread. And as you can see, there are two types of transitions, yes and no, which correspond to the two threads. And here, in this work, we call them roles. And they're basically a kind of abstract threads that can allow us to talk about what does it mean for a trace of a model to be fair, because you need some kind of notion of thread. It is quite easy to see that it's fairly terminating, because basically at each state, one of the two transitions makes strict progress towards the left, and the other one just loops, right? And of course, this model is well-founded. And this is a sufficient condition for the fair termination of a model. And basically, this is kind of a more formal way of setting the argument that I made before about the program without having kind of many transitions that we don't really care about. Now, how do we prove this refinement? Basically, we use kind of standard Iris proof methods. So we have an invariant which kind of looks like this, morally. So we state that the current state of the model, which we can kind of talk about using this circle predicates, matches the kind of the physical state of the program. And then you just do your proof as you would expect. So this is kind of the first use to transport properties from the model to the program. And there is also another use, which is to specify programs. So here on the right, you have the kind of, I think most of us know, the Tower of Hanoi game. So we have 3 stacks of disks, and we want to move them from the left one to the right one. And we want to keep the invariant that no large disk should rest on a smaller disk. And on the left, you have a program that I think many of us had to write when we were learning about recursion, which is a program that computes the solution to this problem. And the invariant, basically it does this by mutating 3 lists, L1, L2, L3, which corresponds to the disks on the 3 stacks. Now, how can we formally specify this program? So clearly it's not sufficient to just specify what it computes, because in the end it just computes a swap of L1 and L3, which we can do atomically. And if we use Trillium, we can kind of prove the existence of a kind of what we call an intentional refinement, which guarantees that the program cannot skip any step and has to do the exponential number of moves to reach the goal, which is not something that you can do with the usual ways of doing refinement in Iris. So far I've been a bit imprecise when I was talking about Trillium. So kind of as is usual in the Iris kind of body of work, Trillium is not itself a program logic, but it's more of a program logic framework, which is parametric in the programming language. And to use it, you have to instantiate it with a concrete program with a syntax and operational semantics, like we've seen just before. Now in case of Trillium, there's another thing you have to do is that Trillium itself only guarantees lockstep simulation between the program and the model. And in practice, it's much too strong because you want some kind of stuttering to be able to abstract things away from the program. And so here's up to the instantiation to kind of relax the notion of refinement to have something that is usable, but still useful. So in the paper, we have 2 instantiations. One is Ferris, which I've been kind of implicitly talking about up until now. So it's a new logic, and the goal is to prove fair termination of concurrent programs. Then there's another instantiation, which is Anaris, which is an existing logic, which was used to prove safety of distributed systems. And we kind of rebased it from the Iris program logic to Trillium program logic. And so now you can prove refinements of distributed systems. But in that case, the refinements are not fairness preserving. So in the remainder of this talk, I will only talk about Ferris. And basically, I will kind of give you a taste of how the instantiation of top of Trillium works and how we kind of use Trillium to prove termination of concurrent programs. So if we start at the kind of the top, at the high level, the kind of basic recipe for using Ferris is that you have a program E, you want to prove that it's fairly terminating. So what you do is that first you find a model M, then using the logic you construct a refinement between E, your program, and this model M, and this basically amounts to proving some Hall triple. And then you prove that M is fairly terminating. Now of course the question is, to use this you have to guess a model M, and it has to be at the same time simple enough that you can prove termination, fair termination, but close enough to the program that you can prove refinement, right? So there's still a lot of work. But on the other hand, it's kind of in a very useless way complete, because basically if you take, for a given program E, if you take the model M to be E, the program itself, then all the steps are trivial in some ways. So like, now I'll explain kind of at a high level how Ferris proves that a program is fairly terminating. So kind of, if you unfold the definition, it means that if a program is, if an execution is fair, tau prog, then it has to be finite. And since we've proved that the program refines the model, you can assume that there exists a model trace which is refined by the program trace. And now we'll see like what we need to know about which properties we need from the refinement to be able to prove this implication. And this works like this. So first, we have to know that this refinement preserves fairness, so that the model trace is also fair. Then we have, by assumption, the model is fairly terminating, so that the model trace is finite. And then we also need that the refinement only allows finite stutter, so that it preserves finiteness of traces. So then we can prove by this kind of detour that the trace is finite. Now before I conclude, I will kind of give you a taste of how this refinement relation is defined under the hood. So let's suppose we have a configuration C. So a configuration is all the threads as well as the global heap of the program. And we have some model state M, and we assume that they're related by this refinement. Now this is not enough information for us, so we have to assume a bit more knowledge. So here we keep track of a correspondence between threads and the roles, which are the labels of the model. Then each thread can have several roles, but each role has a single thread. And each role has a fuel, which is the natural number, so that it cannot decrease below 0. Now let's say thread 1 takes a step, and then it yields a configuration C prime. Now we can wonder which corresponding steps the model can take according to the refinement. So there are two cases. One is that the model does take a step. So in that case, it's row 3, which takes a step. And here it has to be linked with the threads which took a step, right? So only, and then it can get a reward for taking a step. So it can kind of fill up its tank up to some maximum value, fuel max. And this is needed because of step indexing. But however, all the other roles which are related to the thread which took a step have to spend some fuel. And this way, if the thread 1 takes many steps, then all the roles have to take steps, otherwise the fuel will go below 0. And this allows to preserve fairness between the program execution and the model execution. Now there's another case. The model can just stutter. And in that case, to prevent infinite stuttering, basically all the roles have to lose fuel. And the way we define this relation formally is not to have a complicated refinement between the program and the model, but to have a very simple lockstep simulation between the program and a more complicated model, which we call fuel of M. So what happens is that when the user chooses a model M, for Ferris. Under the hood, Ferris gives fuel of m to Trillium, which gives us then a locked step simulation. So here I only talked about Ferris, but in the paper we have this other Aneris instantiation. And the main example is that we have an implementation of single degree Paxos, and we prove that it refines kind of an off-the-shelf TLA plus specification that we've translated by hand. And just, yeah, of the future work, I would just talk about the fact that, yeah, we're working on kind of merging the two and having liveness of distributed systems, and this Jonas doing this. And also, right now, while the logic is modular at the program side, it's not modular at the model side, which is a big limitation. And Igor is working on this. And I'm happy to take questions.
Question? Robert?
Thank you for the nice talk. There was already earlier work on developing an iris-based logic for fair termination preservation by my neighbor here, which funnily in a subsequent paper has also been called Ferris. But could you maybe highlight the differences between that work and yours?
Yeah, so, well, one difference is that we had the chance of doing it after them, so we had the better iris.
Okay, yeah, okay.
So in particular, there's distinction between base logic and program logic and so on. And they had to change the model, I think.
But so what I recall is that the original Ferris was linear. Is yours linear or affine?
No, it's affine. So we didn't need to have linear resources. So we didn't have to change the model too.
What is the trick? How do you make sure that you don't need linear resources?
I think the intuition is basically there's a resource that you don't want to drop, right? In both cases. And here, basically, for each step, the weakest precondition asks you to give it, right? So if you drop it, you cannot take any step. So it's kind of threaded in the weakest precondition.
Okay. I probably should read the paper, or you should explain me offline. I don't immediately see it. But good to know that's fine. I like that.
We have a question online. It says, we are told that the limitation to safety properties is fundamental, but what about transfinite iris?
Excellent question. So in some sense, it's almost kind of orthogonal, right? And the fourth point in the future work is that we think that if we use Trillium on top of transfinite iris, the finiteness restrictions would lift. And the problem is transfinite iris that right now we don't know how to prove termination of concurrent programs, right? Because basically what they do in the paper is that they have a refinement between the program and just ordinals. But then you cannot talk about fairness or anything of ordinals. So I think it's, right now, as far as we know, it's orthogonal.
Okay. More questions?
So I guess these actually two. So the first is about in the paper, and you mentioned above, you have proofs of refinement of TLA specifications. The notion of refinement in TLA is trace inclusion, which is weaker than the notion of simulation that you have. Do you think there would be? Do you have any comments on that? Would it perhaps make sense to have a separation logic based approach based off a trace inclusion notion, or?
Well, I mean, first what we did, that we translated by hand, and then we had just a refined simulation with infinite unbounded stutter, which I assume is very close to trace inclusion. No?
Okay, well, and then the second question is that many of our compiler correctness proofs are based off similar refinement that simulation arguments. I don't think I saw here, but would be interested in the possibility of setting up the soundness theorem for something to a program logic against, say, like the referenced earlier paper, the ComCert semantics that combine these ideas with like setting up a simulation of the ComCert semantics. Did you think about that? Anything along those lines?
Not really. I mean, so this was the motivation of Joe's paper, right? They were looking at kind of one compiler pass. But yeah, I guess it's, on the hand, it would be very nice to have a kind of a new program logic-based proof of concept. I think it's a lot of work as well. And I leave this for other people.
One last question while the next speaker sets up.
There's one online. The one online is, can you repeat how you defined fairness in the model?
So given a trace, right, you have a sequence of roles, which are the labels. And you want to say that if a role is enabled, whatever that means, then eventually it will take a step in the infinite trace. Or it's infinite, or it's finite, of course.
Let's thank the speaker again.
I think someone will take it from me.
Yeah. Thank you. Can you remove that? Thank you. Okay. First, we need to remove this. This cannot be inside of a pocket. It needs to hang outside. Yes, and this must be on your right side.
All right, and for our last talk of the session, Jules will present deadlock-free separation logic.
Yes, indeed. And this is joint work with Jonas and Robert, who are both here. Okay, so our goal today is to make a separation logic for message passing, where you get deadlock freedom for free. And in particular, what we want is that for all programs E, if we prove this trivial Hort triple, then E, when we run it, does not deadlock. Okay. So there are two important pieces of previous work, and that is actress and iris, which is an existing separation logic for message passing, and linear session types, which give deadlock freedom for free. And in this work, we combine those two. So what are linear session types? Well, linear session types are sort of protocol-based types for channels. So here C is a channel, and this syntax tells you that on this channel, you first need to send an int, then you can receive a bool, and then you end. And there are tons of extensions of this with recursion and many other features. But the interesting thing here is that due to the linear type checking, you automatically get deadlock freedom for your programs. And there are no extra proof obligations like lock orders or some kind of well-founded properties or things like that. Okay, so session types are a type system, and those are nice, but they usually give you some kind of standard safety property, whereas with program logics, you can prove functional correctness as well. On the other hand, type systems give you automatic checking, whereas program logics require manual proof. And an important difference here is that in type systems, ownership is usually tied to values. There's no distinction, whereas in separation logic, those two are separate. So let me first talk a little bit about iris, which actress is built on. So iris starts with coq. Iris is built on that. So the first component of iris is heap lang, which is the E in the Hort triple. And this iris likes to construct programs as abstract syntax trees in coq. Then the P and Q in the Hort triple, those are called iprobs and iris. And iris has some very expressive logic for constructing those. Thirdly, we have the Hort triples themselves, which we can state as lemmas in coq. And lastly, we have the iris proof mode, which lets us prove those Hort triples. And then on top of this, Jonas and his collaborators built actress. And this is an extension of iris with message passing. And in actress, you consider programs like this. So we first here create a new channel. Then in the forked off thread, we receive a message, increment it by 1, and send it back. In the main thread, we send the message 2. We receive a message, and then we assert that this is 3. And as you can see, the fact that this is 3 requires the other thread to do the right thing. Okay, so in actress, we have something similar to session types, but extended to be more powerful. So in actress, you have these kind of protocols, which here say that you have to send a natural number. From C, you receive a natural number, and then you send the number that is 1 greater. Actress can also interact with mutable state. Here's an example of that. So here we create a channel, a reference, and then the forked thread will first receive from the channel, increment the reference by that amount, and then send 1 back. The other thread will send the message 2, receive from the other thread, and increment the reference again. And the fact that this at the end produces 3 relies on the synchronization provided by the message passing. And that's why Actress allows you to put separation logic resources in your protocols to be transferred when you send a message. So the problem that we want to solve here is that Actress is not sensitive to deadlocks. So consider our example. If we remove the fork, Actress doesn't care, so you can still prove the same Hoare triple as before. But as you can see now, we receive a message immediately after creating the channel. So the other party is never going to send because that other party is us. You can also have more complicated forms of deadlock, such as on the right. Here we create 2 channels, and both threads do send a message on that channel, but they first receive, so that is also never going to happen. So this raises the question, okay, what does a Hoare triple in Actress actually mean? And for that we have to look into Iris's adequacy theorem. And Iris's adequacy theorem says if you prove such a trivial Hoare triple, then no thread gets stuck, and this is what we call safety. But this is partial correctness, so E is allowed to loop. And if you look into how Actress implements receive, I don't know if it's still true, but originally that was based on a lock, and the lock is a spin loop. So if you write such a deadlock, then this spin loop will be infinite. And this is fine, because it's partial correctness. But in this work, we want to distinguish other loops from being stuck in such a spin loop. So that's our contribution. We want to rule out deadlocking programs such as on the left, while still allowing programs such as on the right. So to do this, we first need a way to state the theorem. And what we decided to do is to make receive a primitive operation, which gets stuck in the operational semantics. And then we have 2 adequacy theorems. The first one is safety, which is similar to the one that Actress has, which says that no thread gets stuck except on receive. In addition, we have a global progress theorem, which says that the configuration as a whole never gets stuck. And actually, we also have a third one, which is actually combined with the second one, and that is that no memory is ever leaked. Okay, to do this, we actually only need to make a few surgical changes to the Actress proof rules. The first change is to make the logic linear. So Iris is affine. Here we need the logic to be linear. And the reason is that otherwise we could drop these kind of send obligations. And if you're not going to send, then the other side might get stuck if they are trying to receive. The second change is that we need to combine new chan with fork. So it's important here that the 2 channel endpoints end up in different threads. And that's why we combine the creation of channels, the creation of threads, with a channel used to communicate with that thread. And the third change, which we are very sad about, is that we need to remove Iris invariance. So this is very unfortunate, future work. But the thing is, if you do this, then the existing Actress proof rules, well, a little bit changed, already guarantee deadlock freedom. So let's look at that. What goes wrong if we try to verify our deadlocking program? Well, the thing here is we only have fork chans, so we cannot even obtain a channel without doing the fork. So this program, if you delete the fork, it's not going to work. We could try to be clever and use fork chan and somehow try to smuggle this channel out of the fork. For example, here we create a reference, and inside the forked off thread, we try to smuggle this channel out via the reference. But this doesn't work. You can also see it's erased, I think. We could try to send the endpoint back via the channel itself. Turns out that this is also doesn't work, because now we are using the channel twice somehow. And that doesn't work. So escape attempts do not work. And this is indeed the key challenge. How do we prove that no escape attempt works? Because we don't want to rule out putting channels in references or sending channels as messages wholesale. We only want to rule it out when, well, as much as possible, we want to still allow it if it's safe. For example, here, this is fine. We have a reference. And then eventually the main thread will set that reference to a channel endpoint. The first forked off thread will receive a number from its D1 channel, and then dereference this reference, which then contains the channel by that point, and send a message back, and then in the other thread, it's received, and we assert that it's true. So this program is fine, and we can prove that this works. So what does the adequacy proof look like? Well, I cannot describe it in detail, but one difference is that in Iris there is somehow one shared resource world for all threads. In linear actress, this is different because there is a separate separation logic world per thread and channel. And they are connected by the ownership. So if a thread holds ownership, an ownership assertion for a channel, they are connected in this graph. In particular, if we have two ownership assertions for the same channel in one thread, inside our logic we can prove that this entails false. But those ownership assertions can still exist in separate threads. That's fine. And the invariant on this graph is that it is, in some sense, acyclic. In addition, to support higher order protocols, which means that we send channels over channels, and to support infinite protocols, our model here is based on step indexing, like Iris. But for the details, you have to look at the paper. So the architecture of linear actress is very similar to Iris. So we start with COC. We have our channelling, which has primitive channels and mutable references. We have actress-style session protocols, which support various features. We have our propositions for the Horde triples without invariance. We have the Horde triples themselves, which we can state as lemmas, and we use the Iris proof mode to prove these Horde triples correct. Finally, we have our two adequacy theorems. Okay, let's look at an example. This was an example already in Actress, and that is Actress merge sort. So in Actress merge sort, we don't use lists, but we use channels. So we send a bunch of numbers on a channel, and then at some point we say, okay, now sort. And then we receive them back, but in sorted order. And this is all done concurrently by somehow spawning channels and threads that handle half of the list. So as you can imagine, this creates a big concurrent mess, but due to linear actress, the deadlock freedom comes for free here. There are no additional proof obligations. The original proof of actress basically just worked. Another question is, can we verify every session type program? And the answer is yes. We have a semantic type system for channeling. And this type system supports mutable references, polymorphism, recursion, and so on. And then we follow the usual Iris recipe for semantic typing. And this then gives us deadlock freedom for session types. Okay, this was my talk. So future work. We would like other concurrency primitives, not just message passing. Of course, ideally, we want some form of Iris invariance. Unfortunately, if you just add the rules of Iris invariance to the logic, then it's very easy to create deadlocks. So we need to change the rules somehow. And another direction for future work is to have liveness, because we here still have partial correctness, which is kind of nice if you want to do a semantic type system, because most realistic languages, they do support loops, and you do not want necessarily to prove termination for all your loops. But it would still be interesting to have a stronger adequacy theorem that is able to guarantee liveness. But this is all future work. Okay, that's it.
Great. So, questions in the back?
Hi, this is really nice work. So I had a question about your APROP. So did you need to like not use Iris and just build your own separation model logic model in order to make it like linear, or is it, are you reusing any of Iris?
We are reusing SBI, but Iris is not yet based on SBI. So in the future, we are reusing something from future Iris.
Sorry, what's SBI?
This is so currently in Iris it's step indexed and it has resources, but this is built in one step. In the future, this will be refactored to first build a step indexed logic without resources, and then build the resources on top of it. We are doing that here.
Okay, thanks.
So you mentioned that the proofs that you were doing in many cases were very easy. It's over here. Yeah,
yeah.
They were very easy. It makes me wonder, could you take the ideas here and be more automatic? So build an automatic program analyzer which analyzes very big programs and either proves deadlock freedom or disproves it. If your proofs are very simple, and I'm reminded of a work by Garagianis and Sergi and some people from Meta who did a POPL paper on disproving deadlock, right? And so I'm just asking, would you speculate about that?
Yes, I think this is possible because I think Ike, who made Diaphragm, already did some experiments for automating actress proofs, and I think that automation should just work here. I don't think there's any additional difficulty unless Diaphragm somehow essentially relies on the Iris being affine, but I would suspect it does not.
So just to be clear, I mean, the input would be a bare program with no spec, and the output would be yes, no, deadlock. Do you think you can do that? I think you can, by the way.
I think with Diaphragm, you would still need to have the protocols for the channels. You would need to give those. I think the rest would be automated. But perhaps I can figure out how to automatically find the protocols.
Thank you for the great talk. May I ask a question? So is this question over? Yeah. So does this work or any other work in the literature try to prove some form of like the completeness theorem that like a reasonably large set of deadlock-free program can be proven within the system? Or do you have any comment or speculation in this regard?
I'm not sure I completely understand the question. Do you mean coupling as in probabilistic programming, or?
No, not the probabilistic programming, but any deadlock-free program can be proven within the system. Completeness.
Completeness.
Not the soundness, but the algorithm.
Well, I think it's definitely not complete.
Yep.
We know examples that we cannot prove deadlock-free, that are nevertheless deadlock-free. So I think there are two reasoning principles for deadlock-free, two main reasoning principles. One reasoning principle is the kind of session type thing, which relies on somehow an acyclicity of a graph that's maintained. You also have reasoning based on somehow log orders, but you can do something like that for message passing as well. And they are incomparable in strength, I think. So perhaps we can combine them to get a stronger logic, but this logic is definitely not complete for deadlock freedom.
Thank you.
More questions?
Yeah, I was wondering if you could please, maybe it's a very complicated problem, but could you speak briefly about what it would look like to get some kind of invariance back into the system? So presumably you're not allowed to put channels in invariance and then forget about them. This is a problem. So
this is a problem. So I think you would need invariance to be linear, but of course those would be fairly useless. So what you could do is, I think, when you fork, that you would be able to duplicate an invariant at that point, but only one invariant. I think it would look something like that, but it's not very clear what it would actually look like.
Thank you.
Actually, I was wondering about that. Could you use cancelable invariants?
Perhaps. I think you would want them to be cancelable, because if your invariants are linear, then it's a problem if they are not cancelable.
There's an online question. There's a tension between guaranteeing deadlock freedom and allowing users to write the programs they want to write. How did you evaluate that second aspect?
Well, I do not really know which programs people want to write, but the programs that Jonas wrote as examples for Actress well, for example, this merge sort that just worked. So, well, I have not done a study of what kind of programs people actually want to write, so that I don't know. Yeah, that's true. So.
Thanks. We have time for one more question if anyone has one.
Yeah, nice work. I wanted to ask, if you don't have invariants, how do you build the semantic typing model of references?
So yeah, in the type system, these references are fairly useless in a way, because they are just linear references. Because if you have nonlinear references, then you can easily create a deadlock by putting a channel in your reference and then dropping it.
All right,
So
thanks.
the theorem would be false if you allowed that.
Right, let's thank the speaker again.
functions and trees of bounded height.
Thank you, Andreas. So this is joint work with Bartek team sitting over here. And I'll start maybe, oh, I see.
Your mic is not on.
Yeah, that's, but I was told not to touch it. So. Okay.
It's pointing down. I think it has to.
Yeah, so point it up.
Yeah.
Okay.
I would ask them to increase the volume.
So I'll begin with maybe some context to tell you that the title sounds a bit technical and down the tree. The context is probably as general as you can get in a theoretical computer science conference, which is deciding if two functions are equal. Okay, so suppose somebody gives you two functions and you want to know if they're equal, and it's meant to be a non-trivial problem as far as decidability is contained. So I would assume that they have infinite domains, so you can't just run through all possible inputs. And the kind of equality is extensional. So for every input, the two outputs are equal. Okay? So this is typically a problem, like I said. If they're like Turing machines, it's clearly undecidable, but it is actually undecidable almost all the time. And there are very few cases where this can be made decidable. So an important example is suppose that your functions have Boolean inputs, so it's also known as languages. And then you want to know if two languages are equal. And a typical situation where you can decide this if they're regular languages. So somebody gives you two regular languages, you can test if they're equal by, building a product automaton and checking if it has the appropriate properties. But if you go slightly beyond regular languages, it doesn't work anymore. So there's very few situations where this can be done. So for example, if you go to context-free languages, this is, for half a century at least, it's been known to be undecidable. An interesting special case is if you take deterministic push-down automatons, like the limits of decidability, proved by Senizerg. But basically, if you think about the inputs being strings, words, then regular languages are almost the only thing that you can do. But now, let's make it even harder, despite it being extremely hard at the beginning. Let's consider non-Boolean output. So they're functions, they're not sets, okay? And here it is even less known. So even if you stick with automata, then there's very few automata models that produce that make this happen. They're typically called transducers. So one example where this is known to be decidable is if you have two string-to-string functions, which are some transducer model. Transducer is an automaton that produces output. The one that's written here specifically, it's a two-way automaton that walks around the input string and once in a while produces an output letter. And this, if you have two such functions, then you can decide if they're equal, but this is a highly non-trivial result. Well, non-trivial result by today's standards. Okay? And now let's make it even harder. And let's try to think of a situation where not only the Booleans, the outputs are non-Boolean, but they have non-trivial equality. So strings have trivial equality, it's just syntactically the same object. But suppose that your outputs are, say, graphs. Then two graphs are equal if they're isomorphic. Okay? I mean, already testing graph isomorphism is a well-known problem. It's not really connected to this work. I don't want to fool you about it. But you can now imagine that it's an even more challenging problem. So you want to check that. So if for every input, the two output graphs exhibit some isomorphism between them. How could that even be decided? Okay? So in this talk, I'll present some results which are about trees, but graphs will appear at the end. And the corollary of it is going to be the first known decidability on Earth, which has a non-trivial example of functions that output graphs, and where the isomorphism is a non-trivial thing to do, and yet nonetheless you can decide if two things are equal. Okay, so that's the context of this talk. So it's about how can you even check if two things are equal. Okay. So now let's get to what's actually being done. Let me move this mouse a little bit. Okay. And so the main contribution is an example where this problem is decidable. And in fact, depending on the representation, because the class of functions is going to be a very nice class of functions, and therefore functions from it can be represented in many different ways. Depending on the representation, this can be non-elementary or it can be polynomial time. Okay, we'll get there in a moment. This is typical for regular languages. You can represent regular languages in MSO. Things are non-elementary. You can represent them by automata. They become polynomial time. It's your choice. Okay. So now I'll get to the situation that we're in. So I'll define the kind of objects that we're going to be transforming, and then the kind of functions that are used to transform them. So the objects are trees of bounded height. So let me just draw a tree. So here's a tree. Okay. Guess there's nothing to explain really. Just terminology, height is the maximal number of edges in the root to leaf path. So I would be interested in trees of bounded height, okay? And they will be labeled, so the nodes will be labeled. This is non-essential, but just will be convenient in some situations. And an important thing, which is actually the title of the paper, the trees are unordered, which means you don't have such a thing as a first child. You just have children. So they're graphs in that sense. And in particular, because these trees are unordered, you can see that there is a non-trivial notion of isomorphism, because you can write down, reorder the siblings, they're the same tree, and that's going to have to be accounted for in the algorithm. So you could imagine that you will produce the same output tree in two different ways, but nevertheless, by reordering it, you get the same thing. So commutativity, as we had yesterday. And here's one way to write it, which actually will be related to the technical development in this talk. You can think of this as this type. If you have some bound on the height of the trees, then there's a set of trees of height at most k with labels from the alphabet sigma. It's like you have a root label, and then you have a multi-set of child subtrees which have smaller height and the same alphabet. Okay? So the multi-sets appear because a tree of height 7 is nothing more than a multi-set nested 7 times. Yeah? Actually, I'd like to maybe remark that the starting point for this research was a remark by Marcelo Fiore, who said that we were working previously on ordered objects, and he said, oh, this is too complicated for me. And it's clearly pulling my leg, but and he said, why don't you work with unordered things and multi-sets? And this seemed to turn out to be a fantastic thing, so I'd like to thank Marcelo for that. Okay. So that's the objects. We have trees of bounded height, so multi-sets of multi-sets of multi-sets of multi-sets 7 times, or 8. Okay. Now, the functions, these are the polyregular functions in the title, but that's just another name for a classical concept called first-order interpretations. Okay. The idea is that this is meant to be the appropriate notion of regularity if you want your outputs to be, is a corresponding thing. Regular languages have Boolean outputs if you want to have other trees on output, and you want them to be polynomial size, and polyregular is what you're going to be working with. But I'll explain it right now, what is, maybe just by example. Okay? So the idea is to use something called first-order interpretations, a classical concept from logic. And what I'll do, I'll just give you an example of a first-order interpretation, and I hope you can figure out what it does. So this particular example is going to be inputting strings and outputting trees. Okay, so despite me not using strings in this talk, the example will have strings, and it will sort of illustrate to you that these trees are more powerful than you would think. Okay, so here's the function that I care about. The input is lists over a 3-letter alphabet, and the output is trees of height at most 2 over a 4-letter alphabet. And here's the function. So the output alphabet is the input alphabet 1 plus a fresh black letter. Okay? And what it does is does the following thing. It inputs a string. Okay? And I guess from the picture you should figure it out. It creates a tree where you have a special root. Okay, just the black root. And then for every string position, you have a node. These are unordered nodes. Okay? So despite them being ordered on left to right in the picture, they're not really ordered. However, what you do is you recover the order by these fake black grandchildren. So the second node will have, well, 0 indexed second node will have 2 children, the third node will have 3 children. And that way, the order is there. So it's uniquely represented. It's injective. So different strings get different trees. And how would you go about consistently? How would you go about defining such a function? Well, you do a loop or something, yeah? And what you'll find is that in the output tree, you have 3 kind of nodes. The root, on the second level, you will have individual nodes in the input string, and on the third level, you will have pairs of nodes. And then that's how you describe an interpretation. You say that the elements of the output thing are going to be something like this applied to the input elements, and then you need to write formulas which describe the structure of your output elements. So you define the output structure, which in the case of a tree is the notion of a parent, and the labels, you need to define it in terms of logic, and the logic that's going to be used is first-order logic, depending on how it happens in the input string. So typically you're going to say grandchild, which is corresponds to a pair of nodes in the input tree, such that the first node in the pair is smaller than the second node. That's typical. You can write logical formulas. So that's first-order interpretation. Okay. So there are functions that input and output structures. In the particular case of this talk, although it can be generalized significantly, we're going to be thinking about the inputs and outputs being trees of bounded height. Okay. And this is a very classical thing, but you can do a lot. Almost any natural syntactic transformation on trees is going to fall in scope of this definition. Okay? So that's the functions that we care about. One simple observation is that they're closed under composition. This is a classic thing from the 1960s or something about first-order interpretations. Here's a slightly less obvious one, that first-order interpretations are the same thing as monadic second-order logic interpretations. Why should that be the case? It turns out on the kind of structures that we're dealing with here, first-order logic and monadic second-order logic have the same expressive power. And that's very nice because first-order interpretations are closed under composition. MSO interpretations in general are not, but here they are. Okay? And I have another theorem in the talk, but I think I will not have time to do it, is that you can characterize first-order interpretation as a certain programming language. Okay, you have to do that. So you have certain types where you have a basic type, then you have products, disjoint union and multisets, you need to nest them, and then you have certain functions to operate on them. So maybe a typical one is going to be multiset union. And another typical one is going to be, this is an interesting one. You have a multi-set of things, and you want to do a loop over it. And the way it's implemented is that for every element in that multi-set, you take it out and consider the rest. Okay? And then there's like however many, 20 other functions, and they give you everything you can do here. An interesting thing is that this expressive power of this language will remain the same if you add higher order features to it. If you add lambda and higher order functions, the same language. And then it becomes a pretty nice and powerful programming language to transform such data structures. And it turns out to be equivalent to first order interpretation. And now let me move to the main contribution about decidability. So the main theorem is that the following problem is decidable. You are given 2 first order interpretations that input and output trees, different heights, different labels, not particularly important. And then you can decide if they're equivalent, which means that for every input tree, the 2 output trees are isomorphic. Okay, and I'll give you a proof. So here it is. In the first step, you reduce to the case, although in general they're first-order interpretations, you can reduce to a case where the formulas are quantifier-free. This uses compositionality of logic. And in the second step, this can be done. You do the following thing. You check if they have the same source code. And if yes, then they're equal. If not, then they're non-equal. Okay, so this is under certain normal form assumptions that you only use quantifier-free formulas, which are types or something. And okay, that would require quite a lot of justification, which is the main contribution of the paper. But it turns out that you cannot write, once you have normalized the code sufficiently, turn it into quantifier-free and there's a normal form that's given in the paper. You cannot write the same function in two different ways. And checking if two codes are the same is a simple algorithm. Okay? But this is highly non-trivial. Nevertheless, it works. And I'd like to maybe just finish with this. An interesting corollary is that if you're into graphs, which maybe you're not, then a corollary of this is that you can lift this result to things, certain classes of graphs, something called graphs of bounded tree depth. This is a well-studied class of graphs. And the trees here are sufficient to talk about 3D compositions and to discuss their isomorphism, which there's no time to discuss that. And therefore, equivalence is decidable for functions which transform graphs of bounded tree width. This is the first non-trivial result about graph transformations that I mentioned initially. Okay? And I think that's all. Maybe what I'd like to just point out that the approaches that we have developed in this paper, they seem to be promising for further work. And there's a number of open problems in this field. And it looks like they could be useful. But I think I'll stop here. Thank you.
All right, questions?
Oh, there's one here.
Go ahead.
Thanks for the beautiful talk. So I was wondering, so since you've bounded the height, I guess the width is the only thing that can go unbounded. Otherwise, I could just check all of them, I guess. So is there some theorem which says that there is some computable width such that if I check up to that width, you're equivalent? Is that the proof?
No. Okay, there's a nasty answer I could give you, which is if equivalence is decidable, that will necessarily be the case. But it's a meta theorem. However, what you're really asking is this the way that you do it? And the answer is no.
So thanks a lot for the wonderful talk. I was wondering about, I personally, I don't really get a good feel yet about polyregular functions over trees of bounded height. So I know polyregular functions over strings. I guess they are subsumed by these guys, right? But
No.
No, not really? Okay. But then why do they have the same kind of names?
We have regular languages of words and regular languages of trees. And
so
I don't know.
The letters kind of subsumes the former,
fat
right?
people and fat buses or whatever. It's
well, come on. So regular languages over trees, so I think generalize regular languages over strings, right?
That is correct, but trees of bounded height do not generalize strings.
Okay.
So there's a more extended answer to that thing. So there's some interesting positive, negative kind of thing. So if you compare strings and trees of bounded height, they're roughly incomparable objects because the strings have a linear order. Trees don't, but trees have other features. And in fact, if you think about it, what's going on here is that trees of bounded height are more general as output structures, but less general as input structures. And therefore, this result is incomparable to deciding equivalence for string-to-string functions.
We have time for one more question, but could we also have the next speaker setting up?
So also thanks again for the great talk. So you talked about, one question would be, this theorem you give, does this actually entail an algorithm which is implementable to actually check this equivalence, given some formalization of in some programming language?
Yes. So once you write the functions in a certain normal form, then the algorithm is just checking if the source code is the same. Normalization can also be implemented.
But I guess there must also be an algorithm to convert these functions into that normal form,
yes,
right?
That is that algorithm. If you start out with a general first-order formula, it's going to be non-elementary, which is tight.
Okay.
Mm-hmm.
But you shouldn't start with that.
Okay, I guess. Thank you.
All right, let's thank the speaker again. So the next talk is by Philippe Heim, who will tell us about how to solve infinite state games via acceleration.
Yeah, it must not inside. It must hang outside. Yeah, and this one must point up like this. So if you don't mind.
Okay. Does this work? Okay.
Yeah, thanks for the introduction. I'm Philip, and I'm presenting work together with my supervisor, Rainer. And I'm going to tell you how we solve infinite state games with acceleration. And to start, like the overall problem that we want to solve is synthesis. So in synthesis, we want to automatically generate some implementation for some system from some specifications such that the system is correct by design. And there are two main directions in synthesis. One is program synthesis. So in program synthesis, what we want to get is some kind of classical program, classical in the way that it gets some inputs and produces some outputs. Yeah, and usually the specification is therefore some relation between the inputs and the outputs, and usually get also you have a grammar that kind of defines what a well-formed program is. And since usually have integers and stuff, right, these kind of programs are usually of infinite state, right? And since they transform inputs to outputs, they kind of represent some kind of data transformation. The other kind of synthesis is finite state reactive synthesis. So there the problem is what you want to get is some kind of finite controller. Think of it as a milli machine, and this finite controller gets some inputs from the environment, produces some outputs, gets some inputs again, and so on, right? It runs over time and gets inputs and produces outputs. And usually because you have this because they run over time, right, you have the specification, some kind of temporal logic. So something like that tells you something over time. And since you have always this interaction between the system and the environment, that the one natural technique that's the main solving technique is via games. So if you have a two-player game that's played between the system and the environment. And usually these kind of finite state controllers are used to synthesize, to model some kind of abstract control. Now, if you think about it, usually most realistic systems have actually both, right? You have data transformation and you have some kind of higher control that kind of runs over time. And maybe that's the first thing, that's the problem you want to tackle, and that's also why we want to look at infinite state games, because it kind of combines both aspects. So in the past, the problem has already been studied, and one main method is there a method that are based on abstraction. So the idea is you take the data that you have, you kind of abstract it to some kind of finite abstraction, and then you reduce this to your finite state method. For example, there are methods to reduce it to kind of finite state games, or to reduce the synthesis problem. If it's formulated and you have a logic that talks about data, you build an abstraction and then you reduce it back to some kind of finite Boolean logic, for example, again, LTL. Another way is to kind of take the classical algorithms, for example, for solving games, and then lift them up such that they can handle the data in a symbolic way, right? So, but both kind of methods have inherently what they kind of do, the main part of the algorithms for example, game solving doesn't differ very much from for the finite state case. And that's why they kind of fail. There's some interesting class of problems with even small examples. I'm going to show you one in a minute where these methods actually fail, right? Okay, so but before I'm going to show you the example, let me introduce you to our formalism. So our formalism, again, that we want to look at now is again a game. It's a two-player game. It's played between an environment and a system. And yeah, so here I have an example. So in this game, right, we have locations, right? And we have variables. There are two kinds of variables. They're input variables. Those are chosen by the environment. And there are these program variables that are part of the state. So they're not directly controlled by the system, but they're kind of part of the state. And then here, for example, then you have guards. So for example, we're in this location L0. And then if x is greater than 42 and the input chooses something that's not for I that's not 0, then we go there. And now the system can choose what kind of assignment it chooses, right? The system chooses between the different updates, we call them, right? So in this case, it can either add I to x or subtract I to x, right? And then our specifications are location-based. So this is the thing that the system has to kind of guarantee. For example, you could say something like some locations have to be reached infinitely often. And maybe let's just look at an even simpler version. So this is, again, it's the same game. And we want to answer the question. The specification is that we want to the system has to eventually reach this location G. And now, how would we kind of solve this? So a bit more technical question that we can ask ourselves is, can the system player, can it always force to reach the set of states that looks like that? So that basically means, like in location G, we kind of accept this is like a symbolic representation over these program variables. So this is like the set of states that we want to reach. And the classical technique to actually compute reachability in game solving is the so-called attractor. Right? So the attractor computation, it's a backward computation that kind of tells you in how many steps, right, in like how many steps you can actually reach the target set. So within 0 steps, of course, the target set that we can reach is exactly the set. Now, within 1 step, the system can actually enforce to reach from L0 if x is smaller or equal to 42. Why? Well, if we are in L0 and x is smaller or equal to 42, then this guard is active. We go there, and then we reach the location G. So within 2 steps, right, the system can reach this target set if x is smaller or equal than 43. Well, why that? Well, if x is smaller or equal than 42, we already know that. If x is equal to 43, and the environment says, okay, it gives us an input that's not 0, let's say 3, right? Then we go here, but then the system can decide whether it adds or subtract I, and for example, if I is greater than 0, so for example 3, the system can choose to subtract I, and then we are again smaller or equal than 42. But now if you continue this argument, you will see, right, so you will get x is smaller or equal to 44, and so on. But this computation never terminates. And the reason is that a priori we don't know how many times we have to iterate that. And like the really underlying problem is here that we have to iterate the strategic decisions between this update and this update an unbounded number of times. And this is what the existing approach cannot handle, because they kind of lift the existing game solving techniques. So now to answer the question, actually yes, the system can enforce to reach the set from here everywhere, from every state. And what's kind of the high level argument here? Well, if x is smaller or equal than 42, and the system can ensure that it can kind of decrement x, like make it smaller, at some point we will reach the case where it's actually smaller or equal than 42, right? And now this is when our acceleration method kicks in. So what we want to now do, right, on a very high level is okay, we know if x is smaller or equal than 42 in L0, we can reach the goal. And if it's not, right, we can go from L0 back to L0, perform some kind of loop, not a real loop, but some iteration, and then in this way kind of decrement. And once we have decremented, right, we know if we can kind of iteration that, at some point we'll reach x smaller or equal than 42. So we can also reach from x greater than 42. So maybe let's just formalize our intuition a bit better. So this is kind of this intuitive statement that we have had, and we formalize this in so-called acceleration lemmas. These are basically this triple of first-order logic formulas, and they tell us, okay, if we start from somewhere, so in this conclusion, and we can kind of iterate this decrement, and at some point we will reach this set of states where x is smaller or equal than 42. Or like a more general version, like if you have some sequence of state, right, and you start in this conclusion thing, and you iterate, you can always kind of, from one to the next part, you always do some kind of step, then at some point you will reach into the base. Okay, so now how do we apply this to our attractor computation? So here we had our non-terminating attractor computation, and here I have a schematic version, right? So this is the first set, this is the second set, and so on. Right, and then we have our lemma, and we first check that the system can actually reach the goal from this base thing, like the base, so the base is actually already in the attractor. This is true. And now if we can check that the system, we also check that the system can enforce to kind of decrement x from L0 back to L0, right? And if we know that, because of the property of this of the lemma, right, if the system can always force to do these steps, if we start somewhere from the conclusion, we will end up in the base. And that's why the system can always also enforce to reach the goal from in this case from top in L0. And so we can add this top to the attractor in L0, right? So this overall part. And that's why and then we also terminate, because we have reached a fixed point. Okay, so now I'd claimed that this is actually the case, right? I've explained on a high level why the system can always like kind of decrement, but like how do we check this systematically? So here again we have our game, and the idea is simple. We use a concept we call the so-called loop game. So this is basically the same game, but we kind of split this L0 location into like a source location and kind of a target location. And now we ask, can from L0 can we enforce to reach the step relation in L0 prime, right? So can we actually do a step from there to there, right? Some kind of loop. That's why it's called loop game. And yes, and we can actually check that again with using our attractor computation. And I mean some handling of the fact that okay, this x prime, this x, right? They have to be a bit different because there's no x prime there. And so we know that the system can actually enforce the step relation from L0 back to L0, so we can apply our lemma. Okay, that's how we apply the lemma. Now you can of course ask, how do you actually get those? So unfortunately, I don't have the time to explain it. But the idea is basically instead of working with concrete lemmas, we work with some uninterpreted lemmas that are made of uninterpreted functions. And then these kind of uninterpreted functions, we collect constraints over these lemmas. And then we use some kind of grammar and templates to use an SMT solver to actually find like the concrete lemmas or sets of lemmas to kind of instantiate those in our acceleration. And the next question, another thing that I motivated this whole thing with synthesis. So I actually want to get a system that we could run. But now how do we actually extract the systems? Also this is a bit, I don't have time for this, but if you have to do these classical extractor steps, you can actually do a very simple bookkeeping, like of checking what kind of steps you do. And if you have these uninterpreted lemmas, right, that we use here, you have to actually do some kind of function synthesis to actually get the concrete lemmas to apply this. And also this overall lemma, the overall quasi-lemma application, you get some kind of sub-procedures for your acceleration. And also like in game solving, I've shown you reachability, but usually they're more interesting, like specifications for games, like for example Büchi, where we have to visit something infinitely often. And the nice thing is these algorithms for solving those, they kind of use the attractor as a building block. So if we accelerate the attractor, we can also accelerate the overall game solving mechanism. But also we also propose a method how to accelerate this outer fixed point, if you know what it means in these game solving mechanisms. Okay. So we evaluated our approach, and the artifact is available if you want to. We compared it to the different these abstraction-based methods to logic-based ones, and some other game-solving-based one. And also here this constraint solvers that allows us to encode fixed point sets. And we compared on the existing literature benchmarks for these infinite state games as well as new ones where you have to actually do these unbounded iterations of strategies. And here's a subset of our results. So these are these are some old benchmarks, these are some new benchmarks. So this is kind of our tool, right? As you can see, right, our tools can still perform well on the new. So we don't actually lose performance on this literature thing by doing acceleration, because we're always doing this explicit step. But we can solve like these new kind of problems that the existing approaches could not solve. That said, like this constraint solver, in some cases actually it can really also yield some quite nice results if the problem is fairly small. Okay, so I think that's from my side. So I hope I motivated and I convinced you that this problem of solving infinite state games is actually an interesting one for reactive synthesis. And I've shown you that our acceleration method with which we can accelerate a attractor and therefore like general infinite state game solving. And also we've shown in our revelation that we can actually also in practice extend the scope of problems that we can solve in infinite state games. Okay, thank you. I'm happy to take your questions.
All right, we already have a first question.
Hi, I was wondering, so the theory that you're dealing with so far, just linear arithmetic so far. So there are quite a few tools, like for example, that are more based on, like basically they try to learn the attractors, right? So I know some of them. So how do they compare, like, if you do acceleration versus doing some kind of learning, for example? How do you compare this? I mean, I think I kind of I found several of them. For example, like Cosynth from I think from Andrei Rebelchenko's 2000 something paper. So how does it compare, like this kind of stuff?
So I mean, for the other game solving, I mean, some of these other game solving methods, for example, they're restricted. So we are not only restricted to integers because we use reals and so on. Like it's kind of independent of the theory. But most of these other approaches, they're either they're kind of restricted, for example, to safety and so on, or as I said, like sometimes many of these cannot also not handle these unbounded iteration things. And and also approaches that kind of, where you actually have as a user, you have to provide an overall template that kind of specifies.
But your benchmarks are only over integers, right? Or
no, we have also benchmarks over reals.
Okay, maybe reals and integers, so like linear real arithmetic and linear integer arithmetic.
Yes.
Okay, yeah. So those ones are easier to handle.
Any other question?
Thank you. So what kind of problems can you not solve?
Well, like if the acceleration argument gets kind of too complex, right? Our tool at some point it kind of, because also we use an SMT solver at some point, we just run into the limits of the things that we can solve. And also like you have to be able, like if you need an argument that has to kind of fit into kind of that grammar that we kind of provide, that we allow for these kind of templates. So, and also you have, since we're using SMT solver, like the arguments have to be in a form that it kind of also, it's kind of can be handled by the SMT solver in a theory form, right? If you start doing stuff, I don't know, with where you would actually need for your ranking argument something where you have like exponential stuff, or you need some very complex like side conditions, right? What has to kind of be invariant under like your loop, right? Then at some point we fail, right? So does it answer your question?
I'm not sure. Also about this step, this is just a technical. Can you go back to that slide where you check? Yes. What does it mean if L0 prime satisfies step this?
This means just
yes.
That you want to reach that in L0, right? We have this we reach kind of the step relation with respect to. So that means like if actually like there's not the step relation per se, but like you have to start that some initial value that you want to see here has to be smaller than x when you're here, and then you kind of have to compute the attract, and at the end see if the x and the initial value like coincide.
Okay, so the initial value is at L0 and then the last one is at L0 prime, right?
Yeah.
Okay, thank you.
More questions? Okay, maybe one from me. What about parity games or Street, Rabin? You handle those?
So I mean, like our benchmarks, we've implemented this thing also for Büchi and Kobüchi. But in principle, you can just, because we accelerate these attractors, you could just implement, I don't know, Selonka's algorithm and then use the accelerated attractor. Right? You could, I mean, there are also cases where we diverge. Maybe this is add where you have to, where this outer fixed points kind of diverges. So like for Büchi, we have some method. We suspect that you can actually extend it to parity also, but we haven't like kind of tried that.
All right. I think it's also worth considering extending this to timed games maybe, which are also often benefit by some sort of acceleration. Any other questions? Okay, then let's thank the speaker again.
Can you remove from your pocket? Okay. So this one hangs outside. First, maybe set up your laptop. Thank you.
All right, so the next talk is by Pascal Bergstrasser, who will tell us about Ramsey quantifiers in linear arithmetics.
And this one must point to your voice. And so, yeah, if you please leave it always. That's good.
Okay, yeah.
Hello, everyone. So this is joint work with Moses Garnadi, Anthony Lin, who's sitting in the audience, and Georg Zetsche. So let's take a look at this example program. We have three variables, x1, x2, and x3. And we say x1 is a real variable. It gets some real input. x2 and x3 get integers as input. We want that x1 is greater 0 and x3 is greater 0. And then we enter a while loop while this variable x2 is greater 0. We add to x1 in each step, 1/2, and then we assign to x2 just the difference of x3 minus x1 floor. So this floor operator means it's the greatest integer that is smaller than x1. So remember that x1 is a real variable. Now one could ask the question, okay, how can we prove that this program terminates? I mean, you immediately see that this should terminate because we just add 1/2 in each step to x1. So this is unbounded in some sense, yeah. And then here x3 is, we subtract x1. So at some point, x2 will go below 0. But one way to do this is to look at the reachability relation we have after at least one iteration. So this can be expressed as a real integer linear arithmetic formula. So this is a formula where you have both reals and integers. And you have addition, you have smaller, and you have this floor operator, as it is also in the program. So the x's are the values I start with, and the y's are the new values here that I can reach. So this formula looks like this. So you have, at the beginning, you say, okay, the x's should all be greater 0. And we know that the third component here doesn't change. Yeah, x3 will always be the same, so y3 is equal to x3. And then we say there exists some iteration n, yeah, such that y1 is, also the new value of x1, is the old value plus the multiple of n, the multiple of 1/2, so n times 1/2. And the same for y2 is just x3 minus the floor of this expression here. So, okay, so this is now a formula. And what we want to do is we want to check if the program terminates. So we ask the question now, does there exist an infinite path in this that is defined in this formula? Like this. So for valuations, A1, B1, C1 for the axis. And as I said, okay, here in this example, this is not the case because the AIs, so the valuations of the x1, they would grow unboundedly, which means that the BIs go below 0 at some point. The setting I want to talk about is, so how can we automatically check if in such a given formula we have such an infinite path. And the other example is a non-terminating program. Here we have only two variables, x1, x2. x1, again, a real variable. Then we say, instead of just adding in each step 1/2, we say we have now 1/2 times x1 plus 1/2, which is also given some input, so it's a lower bound for our input, and then we just assign it to x1. And then we have another input, just gives us some integer that is non-negative, and then we say, okay, we say x2 minus the floor of x1 minus t2. So in this case, we can also formulate the reachability relation again as some linear arithmetic formula. It looks like this. So here, instead of equality, we have now lower and upper bounds on y1 and y2. And you see that, okay, this reachability relation is quite easy because after one step, you can always already reach every state you want. So this is an easy case here. And again, the question, okay, does there exist an infinite path like this? And yes, in this case, it does, because if you start with any value between 0 and 1, let's say 1/2 for your x1, then this expression here, so if the user inputs just exactly the lower bound here, 1/2 times x1 plus 1/2, then this will give you precisely the middle of your actual value x1 and 1. So, and then in the next step you do it again, you get the middle of that and so on. So you have this convergent behavior against 1, but you will never actually reach 1, which means that this floor here will always be 0. Then the user could always also input 0, and then x2 doesn't change. So if you start with some value that is greater 0, then this loop is not terminating. So yes, you have an infinite path here. Okay, and what I want to propose here is that one can use something called the Ramsey quantifier to solve such problems. So the Ramsey quantifier looks like this. You bound you have two vectors of variables x and y that you bind with a Ramsey quantifier, and you have a vector of free variables z, and phi is some formula. In our case, it's linear arithmetic. Then you say that evaluation of these three variables here fulfills this formula if and only if there exists an infinite sequence of valuations ai. So we want that these ai are pairwise distinct, such that phi of ai hj c holds for all I smaller j. So this corresponds to an infinite directed clique in our graph that is defined by the formula phi if we fix the valuation for the set. So as an example, down here, so when we say that x should be smaller than y, then this corresponds to, in our clique, we want that the values strictly increase, but they are still below some upper bound set, which is a free variable. So as in the example before, this is possible in the reals where we have this convergent behavior, but not in the integers, because if you are strictly increasing, then it will definitely be exceeding every bound you take here as a set. And what makes a difference now is that if we take the set here existentially quantified within the Ramsey quantifier, so it's not a free variable anymore, then it is satisfiable because for every pair of x and y's, you can now choose a new value for the set. So you can make the set larger and larger, and then you can still be below it and strictly increasing. So let me come back to our programs here. So for the terminating program, we ask now the question, does there not exist an infinite clique? Yeah? We do not want to have this infinite path. So I talked about infinite paths before, but here you see that in a reachability relation, this is the same as an infinite clique because this is transitive. Yeah? So in general, this is of course undecidable if if in a given formula you have an infinite path, in a given linear arithmetic formula. But that's the reason we are working with cliques here, and it is decidable there. In fact, we can eliminate it. So what we actually want to do is we want to check satisfiability of this formula here. And okay, how do you do this? Well, you just hand it to an SMT solver, yeah? But this does not work because SMT solvers do not allow you to write something with a Ramsey quantifier. That's not allowed. So what our paper here does is it eliminates the Ramsey quantifier in terms of more additional existence quantifiers. And this an SMT solver can handle. Yeah? So we enable us to use actually SMT solvers to check satisfiability of this formula and also to check that the program here terminates. And in the non-terminating example, it's the same, but we don't have the negation here. So here we really want to have an infinite clique. So let me come to our main result. So as I said, we want to eliminate the Ramsey quantifier. So our main result is that if we are given an existential formula in linear integer real arithmetic, then we can construct in polynomial time a formula of linear size that is equivalent to this Ramsey quantified formula. So this means we can eliminate the Ramsey quantifier in polynomial time, and the result will be a formula of linear size. But be aware that we get existential quantifiers, okay? And this was already known that there is an effective elimination procedure for this, but it had much higher complexity. One part of it was that they assume the formula to be quantifier free instead of existential. Yeah, we assume here at the beginning we have an existential formula. And the only way to do this in their method was, okay, we have to eliminate these existential quantifiers. And this is, okay, this blows up. And what we show is that we don't have to really eliminate these, but we can shift these into the Ramsey quantifier instead. And then we eliminate the Ramsey quantifier, and this will give us a better complexity. So let me show how this actually works, so how we can get rid of these existential quantifiers. So here you are given some formula with existential quantifier W. And as I said, in this setting, we can take in our clique for every pair a new valuation for the W. So here in this example, clique it would be, okay, for A, B, we take some valuation U, for B, C, we take V, and so on, okay? So it doesn't matter. So for every pair, we can take a different one. And now what we show is that you can always take some special valuation here. So we extend now the vectors x and y that are bound by the Ramsey quantifier with additional components, in this case v1, v2, and w1, w2. And then we can always choose as the valuation for our existentially quantified variable here the first additional guy here, so v1, plus the second additional guy here, so w2. Yeah, so in this example here, we have now vertices not only with A, B, and C, we have now A with 2 additional components, u1, u2, B, v1, v2, and so on. And now for this edge here, so for this pair of A and B, we can always choose the sum of u1, so the first additional element, and v2, so the second additional element. So of course, if you have such a clique, then you also have such a clique, but the other direction is actually the non-trivial direction. So I think I have a bit time to go into the idea, so how you would prove something like this. So the first step could be, okay, let's take a look at how these cliques actually look like. Maybe we can express them already in like Pressburg arithmetic if we are dealing with linear integer arithmetic. But then you will notice, okay, there are formulas like this, where you can have y is greater than 2 times x and some additional restriction on the x. The problem here with this formula is that in your clique, this forces the clique to grow exponentially. And this is something you cannot express in Pressburg arithmetic. But what our strategy will be is that the existence of such a clique is equivalent to saying, okay, there exists such just an strictly increasing sequence, such that for all elements of the sequence, this additional restriction psi holds. And this now can be expressed. So this is just, an increasing. It's just a smaller symbol, right? So we can express this. And the idea is to, okay, so I mean, one direction is clear. If you have a clique in here, then you also have a strictly increasing clique. But the other direction also, if you have a strictly increasing clique, then you can take a sub-clique of this, so an infinite subsequence, such that this fulfills this. But we will not express actually this infinite clique in the first formula here. So let's really quickly look at the idea. So let's say we have a conjunction of inequalities. On the left side, we are talking about the x's. On the right side, the y's, the free variable z, and some constants. And what we do is we actually guess a vector of integers that can also be omega, so we can also guess this if a symbol should be omega. And then we want them to be guessed like how these left and right-hand sides evolve during your sequence. Yeah? So you guess actually an upper bound of the supremum of the left-hand side and the lower bound of the lim-inf of the right-hand side. And then we showed that there is a condition which is called compatibility. So such a sequence is called compatible with this profile here. So this is sequence, this tuple. If and only if it had this shape, and we also want that it is admissible. Yeah? We want that these values here are smaller than the others, so we want that in some sense these lower bounds here are smaller than the upper bounds, and then we can fulfill this inequality here. So we show that the Ramsey quantified formula is equivalent to saying there exists an admissible profile P such that there is a sequence compatible with P for C. And this can now be expressed in linear arithmetic. And one key feature here is to restrict to sequences of a special form where we have some initial vector A0 and then we add some multiple of another vector. So one can show that this actually suffices, and then you can express this condition here with the help of matrices, essentially. So let me quickly show you some applications where we, with our result, get complete complexity results. So one thing is linear liveness. So we have already seen some sort of liveness in this termination, non-termination example. But so linear liveness is the problem of, so you're given some system and you want to check if there's an infinite clique or an infinite path in the system, in the reachability relation of that system, such that you reach some state infinitely often in it. Linear liveness means, okay, you can also say that some formula should hold between every pair of this sequence. So this is a bit more general. even, and we show that this is NP-complete for various systems, like continuous VAS, reversal bounded counter machines, Parrig automata, and succinct one counter automata. And the key feature here is that in all of these systems, we can actually compute this reachability relation in polynomial time. And if we computed this, then we can add the Ramsey quantifier, eliminate it, and then we get an NP procedure here. And if we check satisfiability, then what's also can be done here is checking if some given Pressburger formula, quantifier 3, is a well quasi-order. So here you can imagine, so you want to check if there is some infinite descending chain. Essentially, and this can be expressed with Ramsey quantifiers. We showed that this problem is co-NP complete. And also, one application, this may seem a little bit unrelated, but one can show that the problem of monadic decomposability is co-NP complete. So what does this mean? So monadic decomposability, you are given a formula with multiple free variables. And now you want to check, can you somehow decouple these variables? This means, can you somehow find an equivalent formula such that it is a Boolean combination of unary formulas, formulas that only have one free variable. This means you completely separated those variables. And here, where the Ramsey quantifier comes into play is where you check if an equivalence relation has finite indexes, actually. And this can be done. Yeah. And that's it. Thank you.
All right. Questions?
So, what aspect of integer arithmetic is crucial here, besides the fact that there is elimination?
What do you mean with integers?
Yeah, linear integer arithmetic. For example, so your motivation was integer program, but I can also think of it as I can also probably come up with a program which has uninterpreted functions, and then I can define a well order on that domain, on a domain, and then I can ask the question: is it the case that this program terminates? I can translate the same question to a Ramsey quantifier formula, but this time it won't be integers.
Yeah, but in the proof we heavily use the facts really that we are dealing with integer or real linear arithmetic formulas. So like in this shape, yeah, where we have these inequalities, and then we are doing some stuff with Ramsey's theorem where we can get like subcliques, and yeah, I'm not so sure. Of course, one natural question is, so how does this work for other theories like EUF or whatever you're talking about? But yeah, at the moment we don't know.
Okay. And the other question is, so there's this thing called integer linear loops.
Again?
Linear loops.
Okay.
Where you have it's like a while, some condition, some linear condition, and then the loop body looks like a linear transformation.
Yeah. So it's similar like this, right? But
without
the problem is that you want that the reachability relation is expressible in linear arithmetic here.
So there but it's just a linear transformation. X is equal to A is a matrix multiplied by X.
Yeah, but the transitive closure is a problem, right?
Okay.
One step, okay, yeah, I give you that, but transitive closure, no.
Thank you.
Any other questions? Okay, let's thank the speaker again then.
So this one must be...
All right, and the last talk of this session will be given by Ramanathan Thiniyam, who will tell us about reachability in continuous push-down VAS.
Okay, so does that mean... Can you do it on this side?
Yeah.
Is that okay? Okay, so hi, I'm Ram. This is joint work with Bala, Rupak Majumdar, and Georg Zetsche. Most of this was done while I was at Max Planck. Now I'm at Uppsala. Yeah. So maybe I'll just go over the title bit by bit so that you understand what the problem is. Reachability in continuous pushdown VAS. So to begin with, what are pushdown VAS? So before we go to pushdown VAS, maybe I'll just talk about what are VAS, right? These are vector addition systems with states. So you can think of this as a model where you have finitely many counters. So here there's 4 of them. And there's finitely many global states. So here's Q1 through Qn. And there's some finite set of rules which says you can move from some state to some other state while removing tokens from the counters. So here, for example, we moved from this configuration where we were in Q1 with this things in the counters, and then we moved to Q2. So here we applied this rule where we subtracted 1 from the green counter and we added 1 to the blue. So here it's important that the counters are required to stay non-negative always. So for instance, if you had no green tokens at all, then we could not have applied this particular rule. So from a program standpoint, you can think of VAS as modeling regular threads with asynchronous calls, right? So each thread is very simple, it's finite state, but you also have dynamic spawning, so you can spawn. And of course, the assumption is that there's some finitely many different states in which you can be. So this means that with a finite number of counters, you can keep track of how many threads are there at any given point of time, right? So it's a very, let's say, central model of computation. So what's pushdown VAS? What you would expect, right? So it's VAS equipped with 1 stack. I think it's well known that if you just have 2 stacks, this is already a model of computation which is Turing complete. But here, so we have 1 stack and you have a lot of these counters which are VAS counters. So with this, you can model programs where you have 1 thread which is also allowed recursive calls. And so this means you can sort of abstractly, you can push or pop on the stack, while at the same time you can add or decrease to and from the counters. So formally, this configuration of a PVAS is a tuple, which is the state Q, and there's a stack content, which is W. And then there's the values of the K counters, some N1 through Nk, which are numbers. Okay, so here is an example. So, so here's a PVAS with 2 counters and stack alphabet AB. You have 4 states, Q0 through Q3, and the edges on the labels on the edges are transitions. So if you look at T1, so this says decrement the first counter by 1, do nothing to the second counter, while pushing an A on the stack. Right? So if you have on some edges, I have an A bar or a B bar, so that stands for a pop, whereas just the A or the B stands for a push. So here, if you have a current configuration, which is, let's say, Q0, some W, N1, N2, where N1 is strictly more than 0, then using T1, we can move to the configuration Q1, WA, N1 minus 1, N2. So sometimes we just write the configuration more succinctly as QWV, where we sum vector of counter values. We also define this ordering relation on on vectors, so V and V prime. So we say that V is less than equal to V prime if V prime is at least as large as V in each coordinate. And we extend this notion to configurations. So where the state and the stack content is the same, but the V is smaller than the V prime. So that's just about the model. So the next thing is, what is reachability? So this is a very central sort of problem in most models of computation, where you ask, there is some configuration Cn, and is it reachable from a configuration C1? And we say it is if there is some sequence starting from C1, so C1, C2, ... till Cn, such that for each Ci, you can transition to the next configuration Ci plus 1. There is also a related notion, which is coverability. This is where our ordering notion comes into play. Right? So it's similarly you have going from C1 to Cn, you have a sequence of transitions, and then you say that a configuration Cm is coverable from C1 if this final configuration Cn is at least as large as Cm. So often the coverability is used to model things like just reaching some part of the state, right? Like just the global state and the stack, where you're not interested in how many things are in the task buffer, this kind of thing. So usually it's an easier problem than reachability. So let's just quickly see what these things look like in our example. So Q2, comma epsilon, so epsilon is just an empty stack. 0, 3 is reachable from Q0, epsilon 1, 0, right? So first you can go from Q0 to Q1 via T1, and then you go from Q1 to Q2. So that corresponds to these two transitions, right? So you go from Q0, epsilon 1, 0, you decreased this first counter by 1, you pushed A onto the stack, so you get Q1, A, 0, 0, and then you can take the next transition where you don't do anything on the counters and you pop this A. So you get to Q2, epsilon 0, 0. Now you can go back from Q2 to Q1 while adding to the second counter and pushing an A. So you go to Q1, A, 0, 1. So now you can see that you can sort of go back and forth, and you can, after 2 more cycles around this loop, you will get to Q2, epsilon 0, 3. So note that Q2 epsilon 0, 3 is not reachable from, for example, Q0 epsilon 0, 0, because, as I said, you cannot go below 0. So you cannot fire either of these transitions, T1 or T2, right? Because you need something in either of these counters to go to the next thing. So what about coverability? So Q2 epsilon 0, 3 is coverable from Q0 epsilon 2, 2, right? So you can take a similar kind of sequence of transitions where you go from Q0 to Q1, and then Q2, and then Q1. And so finally, what you can do is you can reach Q2 epsilon 1, 3, so which is a bigger configuration than Q2 epsilon 0, 3. But note that you cannot reach Q2 epsilon 0, 3 from Q0 epsilon 2, 2, because you will never be able to remove the second initial token which is present in the second counter, right? So there's only this one time that you decrement, right when you go from Q0 to Q1, and then after that, you can't take away the remaining token which is still there. So which means that you can't reach it, but you can cover. So I just want to talk a little bit about the fact that these kind of problems, the reachability problem, just for VAS to begin with, is already known to be really difficult. So only very recently it was shown that reachability for vector addition systems with states is Ackermann complete. This means that essentially this Ackermann is a function which grows faster than any fixed tower height of exponentials. So this is a function which grows crazy fast. Even the coverability problem is not very easy. So coverability for VAS is known to be exponential space complete. So obviously, the general case of PVAS, it's something which is more, you're adding a stack to a VAS, so it inherits this Ackermann lower bound from VAS. And the decidability of reachability in PVAS remains open despite our best efforts, even for just one counter and one stack. And so in the theory community, this is an object of central concern with lots of people wanting to see what happens. So naturally, there has been a lot of work on approximations because this is a model which sort of combines sequential computation, that is a stack, with concurrent computation, which is counters. So the track that we will take is that of continuous push-down mass. So what is the continuous approximation? So a continuous PVAS is one in which if you have some transition, then it can be fired fractionally. So here, when I say fractionally, I'm only talking about the counters. I'm not talking about the stack. The stack is always discrete. But if you have like a -1 +1 on 2 counters, then you can, let's say, fire this by half. So in general, this firing fraction is some rational number. which is in open 0, close 1. And you can choose this independently at each step. So here again, going back to our example. So if you fire T1, this transition T1 with fraction 0.5, then you can reach Q1A 0.51 from Q0 epsilon 1, 1. So this also means that you can cover Q1A half-half from Q0 epsilon 1, 1. But note that you cannot cover Q1A 1, 1 from Q0 epsilon 1, 1 because of the fact that you can take some very small fraction, but it's going to take something away, right? So that's why it's open 0, close 1. Right, so this has some history, so I'll just briefly mention. Continuous approximations were first introduced by David and Ala back in '87, in fact, for Petri nets. Reachability was shown to be P-complete for Petri nets by Fraka Haddad in 2015. And then in 2017, it was reachability for continuous VAS was shown to be NP-complete. So roughly the difference between Petri net and VAS is the addition of discrete states. And this seems to somehow give you this jump, right, like from P to NP. Despite this, this is a massive reduction in complexity. So it's much, much better than Ackermann and so on. And in particular, it allows for use of SMT solvers for these kind of problems, at least for the C-VAS case, continuous VAS case. So a natural question was, if you add a stack, how much more does this problem get? How much more difficult does this problem get? And our theorem shows that reachability for continuous PVAS is non-deterministic exponential time complete. So the result is very robust. In particular, the lower bound already holds for a model which can do exact counting up to an exponential number, along with continuous counters. So this was, let's say, against the grain. I think for a long time we were hopeful that this problem would be in polynomial space for reasons that I will not get into. So I will now go into a brief overview of the lower bound and possibly skip the upper bound entirely. And again, the reason I want to go into the lower bound is because I feel that this was the somewhat more surprising result for us. Okay, so here is the chain of reductions that we use. So there is a bounded version of the post-correspondence problem. So PCP is well known to be undecidable. There's a bounded version which is known to be an X prime hard. And so we start from there, and then we proceed through a chain of reductions. So we go over to, so this is a very descriptively written model, but it looks a little bit scary. I'll tell you. Okay. I have 2 minutes left. Okay, so then maybe I should choose to show you one part of this. Yeah, okay. So let's say that the first step is not really very difficult. So let's just look at this model, which is the 2. So it's a 2CM RL.2 plus 1 is a 2-counter machine with, so the RL stands for run length bound for the reachability. And you can multiply by 2 and you can add by 1. And the problem we consider is equal reachability. So you can sort of think of, in PCP you have 2 strings which need to be the same. So that's how you end up getting equal reachability for this model. So this other model is very close to continuous VAS. So here you have 0 testing. You still have a run length bound. And all things are constrained to be, all counters are constrained to be in 0, 1, right? So, so the goal is to simulate this 2-counter machine with dot multiplied by 2 plus 1 using one of these machines. And so here you note that the largest counter value attainable is 2 to the m. So you can represent, the idea is to represent a number occurring in our 2-counter machine m as n by 2 to the m as this fraction. And we solve the goal. I mean, we have these two challenges. First is we have to somehow create this exponentially small number, which is like 1/2 to the m inside a continuous counter. And we also have to simulate addition and doubling. So roughly speaking, the main idea is somehow using the zero tests, you can control the firing fraction, right? So this fraction, you can force it to be 1 by using zero tests. So, and then the second part of it, which is moving over from this restricted sort of 0, 1 fractions to CP-VAS, uses this idea of using exact counting in order to simulate multiple zero tests. So in particular, the crucial thing here is that we can in fact show hardness for just the CVAS model with a run length bound which is in binary. So all we do with the stack is just count, that's it. And so this means that, so this basically means that even if you have, for example, a Boolean global state, right? So then you can count up to an exponential number inside this with a bunch of Booleans in the global state. So already for a model like that, you would have this lower bound. Okay, so with that, I skip the upper bound as well. So to conclude, we showed that reachability, and in fact, we can show that even coverability for CP-VAS is non-deterministic exponential time complete. It would be interesting to add continuous counters to more powerful models, such as higher order push-down automata, and see whether we can get decidability results. It is, I think, equally interesting to study more restricted models in the context of continuous approximation and see if we can get better complexity, hopefully like in P space or NP, so that we could actually put it to use. Yeah. Okay, thank you.
Questions?
So you started off with the analogy of asynchronous programs with VAS, and then what would CVAS correspond to in a programming language setting?
Yeah, where you have like just one thread. So you can think of it as yeah, you just have one thread which is allowed to do recursive calls.
But this fractional firing?
So the fractional firing, as I mentioned, there are two parts to it, right? So one is where you have the VAS model and then you add one stack to it. So this is push down VAS. And then the continuous part of it is this sort of over approximation where you are allowed to fire the count, whatever you do on the counters, you're allowed to fire that fractionally. So now you have sort of rational values on the counters, but the stack operations are still discrete. Because it doesn't make sense to say I push half an A, or at least we couldn't think of what that would
So mapping it back to asynchronous programs, there's no direct mapping except for this approximation thing that you're saying.
Yes, I would say so. Yeah.
I see.
So there are with just the CVAS without the pushdown, people have used it, have implemented this, and it actually does quite well. I mean, yeah, practically speaking, it does quite well as compared.
Can I ask one more question?
So long time back, Rupak and Ranjit had this result that you could do some kind of under approximation, over approximation with bounded counters, and with a small bound, you can detect that you have actually finished, and you can actually say that nothing else is reachable. I don't know if you know this kind of result, but it made this whole thing, possibly practical because you could implement that algorithm. Are such bounded counters and detection known for such problems as well? And have you looked at that?
No. So if you bound so there is no continuous aspect to this. This is just a bounded counter. So it's just like a global state and bounded counters. So yeah, I mean, so then in essence, this is somehow a succinct version of a finite state machine, right? Because
no. It's the original problem, except so in general, there is a very large bound, such that if you search up to that bound, it's okay. But in practice, so it could be much less, and you can detect if it's much less. It can be 2 or 3 even.
I see.
And then you detect it, and they showed that for some practical systems it was possible.
So I'm not sure how this would how this corresponds to the original model, because so the continuity in the larger scheme of things, it's nice. But with this run length bounding, one of the things that you see is if you take the same run length bound and you just directly apply it for a VAS without the continuity, then you can keep track of everything in p-space.
Well, this is exploiting the instance complexity rather than the burst case complexity.
Okay.
So.
Right. So you just mean in terms of implementations, whether you can look at, yeah, okay, thank you.
I was just wondering whether you think this kind of continuous approximation approach, whether you'd be able to get results told in the setting of, well, I'm not sure if they exist, but branching push-down vector addition systems, where you have the kind of branching construct.
Yeah, I think there is, yeah, I think there is a likelihood that there is some very general decidability result which is there in this, for this particular model. So we are looking at it, and I mean, it would be interesting. At this point, we are positive that something would come out of it, but regarding complexity, it's quite unclear how bad these things would be, yeah.
So, okay. Are there any questions? Go ahead. Okay. These executions with the fractional firings can also suffer from, I guess, xenoness.
Sorry, what is xenoness?
Where you keep decreasing only by half.
Yes, in fact, so okay, so that is part of the reason why certain things work well. In fact, so what you can do is, if you're interested in, for example, just reaching some particular global state, there are some ways in which you can sort of drop the fraction by half at each step, and then you can sort of saturate certain sets of counters that you want, and then you can go somewhere, you can desaturate. There are certain things, interesting things that you can do. So that's part of the reason why certain things are easier.
So if I restrict my model to be only only non-Zeno runs, then this complexity would be hard to get.
So by that, do you mean that you want to restrict the numbers to be, let's say, sub-exponential in some sense?
I mean, that's one way to say, but I could just say the semantics of my CVAS is that all runs are non-Zeno. And then under this model, the reachability would
possibly be. So this is not clear. I mean, what would happen? This is not clear. Yeah.
Okay.
Yeah. So yeah. So especially the upper bound, which I didn't go into, it uses a lot of the previous technology from Blondin and Hasse, who studied the case without the stack. And there, it's so the main content of the upper bound over there is a lemma where they show that every run is characterized by 3 different runs, where you just go from one place to somewhere, and then over here you are allowed to go below 0 in the middle run. Then here you are again. So there is a certain way of, and it's important for that particular characterization that you are able to somehow pump runs by repeating it, making small fractions and repeating it multiple times. So it would be interesting to see, if you disallowed those kinds of behaviors, then what would happen?
Thank you.
All right, let's thank Ram again, and that's the end of the session.
Okay.